Total 9 students are there. So, Professor Narendra here from CMR Institute of Technology, and as per the AICTE initiative, we are going to conduct the GATE classes for the civil engineering courses, and this is for the 5th semester and 7th semester 2 years program, and this classes are designed to support the SC/ST students for the higher education, so they can take interest in the higher education, and we can promote the studies for the further studies purpose, and people can go for they can clear the GATE exam and they can go for the masters and MS and all that. So this is the initiatives and funded by AICT. All India Council of Technical Education has funded this program, and then we are going to conduct the classes. As per my expert domain, I'm from the environmental engineering background, so I'll be talking about from the GATE perspective point of view. I'm a professor here in CMR Institute of Technology, so I'll be covering the GATE perspective, and from the GATE point of view, we'll be talking about the environmental engineering aspects. Basically, we'll be having two things here. One is the environmental engineering first and environmental engineering second. So we'll be talking about the water mainly, so water and wastewater engineering. So as per the GATE syllabus is concerned, if we go in the GATE, we'll discuss about the GATE. Like in the brief, we will talk what is GATE and actually and how much marks content is there, what is the pattern of the exam and how it will be conducted, right? And what is the percentage coverage in environmental engineering for this GATE, and how we will cover all the modules and all the topics from the GATE point of view. So it's a national level exam, and to promote the higher studies nowadays, major industry, and you will be based on GATE. So there are the two opportunities. Either you can go for the higher studies. Akash, can you hear me?
Yes, sir.
Is it audible?
Yes, sir.
Before starting, I want to ensure that everyone is listening properly. Okay, fine. So that's, as I told you, this is a national level exam, and you'll be having two types of opportunities. Either you can, if you get a good score, you can do your master's and take in various specialization. And if we are talking from the civil engineering point of view, either you can go for structural engineering, you can choose water source engineering, you can go for construction technology management, you can go for environmental engineering specialization, or you can go for the GIS in remote sensing sector also, and geotech also you can move. So there's a lot of 7-8 specializations, so you can do your masters in all IITs and including NITs also in ISCs. So you'll be having a good opportunity to explore in the research field. uh, and another thing, if you want to get a job in PSUs like IUCL, HPCL, all these ISRO and NTPC are also taking the recruitment for this only through the GATE. And you can go in HPCL also. You can join ONGC as an assistant engineer, as a graduate engineer training. So there are a lot of opportunities through the GATE nowadays. Uh, so once you get a good score, now we'll discuss in briefly how much score is required in all that. Then I will come for my sector, environmental engineering domain. Then we'll discuss about the environmental engineering part. Okay, so in 2021, IIT Mumbai is conducting this exam. There will be 100 marks exam for the 3-hour duration, consisting of 65 marks, and there will be the mm, division of marks here. So there's a multiple type of questions. The IIT Bombay has made several changes in GATE exam 2021 pattern of questions, and the GATE 2021 will be completely objective type. The new GATE exam patterns questions will include a new category of the questions, MCQ types, where the remaining questions might include multiple select questions and or numerical answers types questions. Marks distribution among the sections has been also changed. So there is a general aptitude. We'll be covering number of 10 questions consisting of 15 marks. Engineering mathematics, um, again 13 marks, 12 to 13 marks. It keeps varying till 15 marks also. It is 15 to 13 marks. They can based on the weightage. And there is a subjective bias question, your technical domain related to civil engineering. There will be 55 questions consisting of 72 marks, and the total number of questions will be 65 for the 100 marks questions. Okay, so there will be 1 to 25 will be the MCQ single correct answers, and then there will be some subjective types of questions where you have to solve the numericals, and there is one column given there. You have to put the number itself. There is no MCQ questions available there. There is a subjective types of questions, 5 to 10 questions. 5 questions you can get it as subjective type of questions, and you have to put the answer in a. You have to solve it this numerical and put the values. The objective of these GATE exams is quite different from your subjective studies. If you see that in previous year GATE exam paper, they are very much keen about the concept and accuracy. So rather than reminding you the numericals and solving the big if you are going to do that, they don't that much of things. And too much of numericals, too much of formulas, too much of derivation they don't want. They need to check your concept actually with the accuracy. So the objective is quite different. If you are studying in civil engineering program BE courses, if you are thinking like I have solved a lot of numericals and I have done all the iterations and big formulas I have reminded, then sometimes it doesn't work because they need to check the concept. So concept based studies they will focus more, and they need to check your thoroughly concept, the basic concepts only, uh, as per the UG knowledge levels. So if you are good in that, if you are good in accuracy, if you solve the numericals with the accuracy, with the certain time limits, time management also play a very important role, then it is okay to achieve a good marks in GATE exams. Okay. So if I'm talking about the environmental engineering perspective, so environmental engineering, we have a weightage for water supply engineering 5 to 6 marks. Questions can come. Wastewater engineering 3 to 4 marks. Solid waste management, air pollution and noise pollution control all together will contain a 1 to 2 marks question. Okay, so major weightage we are having a water supply and wastewater engineering. So I will be covering 2 lectures for the wastewater and water supply engineering, and then I will move for the solid waste and air pollution control. So this is the detailed syllabus for the water supply and wastewater water supply engineering. If these are the topics that I'm not going in a details, yes, we have to quickly get the concept. Once you get the concept, how you will use this concept in terms of numericals or in terms of concept generation also. So you can quickly remind that particular concept and you can implement it easily. So we are not going for the subjective studies. We are just quickly remind the thoughts, whatever we have studied, or if you have not studied water supply engineering also, then you can understand through these studies. Okay. So we'll be talking about the public water supply schemes, water demands, per capita demand, population forecasting methods, and we'll be talking about the hydrological cycles, precipitation, rainfall, index of wetness, what is runoff, sources of water, right? Intake for collecting surface water sources, and the conduits for transporting waters, open conduits, we can say the open channel as well as the closed channel conduits flow. And we will be talking about the flow in pipe systems, various hydraulic parameters, various hydraulic like the velocity of flow, discharge, and everything we will calculate it. And we'll be talking about the pipe network also, how to design a pipe network, the distribution network, how to design it, what are the hydraulic parameters that you have to take care and how to design it. We'll be talking about the pumping stations, lifting pumping stations, distribution network, as well as the transmission line, both we will be covering. Okay, what type of pumps we are using it, what are the efficiency that you need to calculate it for the pumping station, mechanical efficiency, electrical efficiency, and overall efficiency of the pumps, how to put the pumping stations. We'll be talking about the quality control of municipal and industrial wastewater, analysis of water, that whole design will complete in this, and water quality standards. The water quality standard will cover the water quality characteristics report. We have to check the various physical, chemical, and biological parameters of water as well as the wastewater. So wastewater and water characteristics, we have to check it, and how to determine that, how to do the test in a water laboratory and environmental engineering laboratory, and how to get the value of various physical, chemical, and biological parameters. That will talk about it. We'll be talking about the various, if we are not going to treat this water, if we are not going to treat this wastewater also, what are the diseases, what are the impact on the environment, what are the waterborne diseases, and what are the hazards that we have it, so and how to control it. These all the things we'll be talking. We'll be talking about the various methods of treatment, primary treatment, secondary treatment, and tertiary treatment in terms of wastewater, if it is, and if it's a municipal water supply, then we'll be talking about the primary treatment as well as the secondary treatment. So the various unit operations we will be talking, and there's coagulation, sedimentation plant, coagulation quantities, right? The complete water treatment plant units, all the unit operation and sequence we will be talking. We will be talking about the sludge management also. And then, as I told you, the distribution, the complex pipe network, we will be talking about the distribution of the water network. Okay. In the same way, we will be moving, if we are moving for the comprehensive what are the hydro to take, and factors of a sewage network. And there's a first, as I told you, this we'll be talking about the planning histories of the sewage, and then once you study about it, then we will move for the quality aspects, wastewater quality aspect. Again, it will be the same analysis for the physical, biological, and chemical characteristics of wastewater. Again, certain changes will be there, so because wastewater is quite complex, so the physical parameters and chemical parameters and biological parameters will be getting higher values. So, but the test methods and everything will be same. If you are going for the BOD test, UD test, pH, if you are going for the color, taste and odor, turbidity, all the environmental, we can say the characteristics, you can do it in a laboratory. Okay. And then I will be talking about the comprehensive sewage treatment plants, again unit operations, primary pre-treatment, primary treatment, secondary treatment, and tertiary treatment, like this, and advanced treatment process also. And then briefly I will be talking about the sludge management, the sludge which will be coming out through the whole comprehensive sewage treatment plant, maybe from the pre-treatment, primary treatment, and secondary and tertiary treatment. Everywhere sludge will be generated, and it will be collected through the Devotee settlement on the bottom. And sludge will be having a lot of toxic and hazardous chemicals also. That sludge treatment is also required. Sludge treatment and disposal methods. Okay. So briefly, I have spoke about it. This is your syllabus as per the GATE is concerned. Environmental engineering, water and wastewater quality and treatment. Together, we have to study this thing. Basics of water quality standards, physical, chemical, and biological parameters, water quality index, unit operations and processes, water requirement, water distribution system, drinking water treatment, sewage system design, quantity of domestic wastewater, primary and secondary treatment, effluent discharge standards, sludge disposal, reuse of treated sewage for the different applications. And then second, as I told you, this will contain 5 to 6 marks. Remaining 1 to 2 marks will be the air pollution as well as the municipal solid waste. So once I will finish this portion, I will be moving for the municipal solid waste. if you are in 7th semester and in 5th semester, might they have not studied about the municipal solid waste and air pollution, but if you are in 7th semester, you must have completed all these things, air pollution and municipal solid waste. Last semester we have taught this municipal solid waste. So I'll be talking in the next module or next classes about the municipal solid waste and air pollution together. And air pollution I will be covering only the type of pollutant, their sources and impact, air pollution control, air quality standards, and air quality index and limits. You are not supposed to study everything about environmental engineering. Whatever the topic is especially mentioned, that only you have to cover it. Rather than there is no big syllabus. If you we can say specify your domain, if you because most of the subjects are correlated. If I start from the water, means wastewater will also come into the picture. If I start from the wastewater, then industrial wastewater will also come into the picture. And most of the characteristics are quite similar. So you have to correlate the subject, right? And then municipal solid waste. We'll be talking about the characteristics, generation, collection, transport of the solid waste, engineering system for solid waste management, reuse, recycling, energy recovery, treatment, and disposal. Okay, so these are the things we will be covering. So I'm coming for the environmental engineering first. That I will be talking first about the municipal water treatments and municipal water supplies, treatment, distribution, design, as well as the disposal. So all four parts I will be covering here. So first you have to understand the sources of water. What are the sources are available for the water? We will be having two types of sources mainly. One is the surface source, another is the subsurface source. Yeah, you can say the underground sources, right? So if you see the surface sources, you will be having a pond, lakes, stream, rivers, storage reservoirs. Oceans are also generally considered in under the surface sources, right? And presently it is not used for the water supply because the water is very saline in nature, salinity is very high, very alkaline in nature, and turbidity is very high. So we are not using ocean water. If you are going to treat this ocean water, that's a very costly affair. Okay. Then if you are going for the desalination plant and all that, it is very costly. So if you are going to use the surface water, you will be having a wells, right? All underground under this. So what are the basics of water quality standards? As I told you, we will be having a sources we have studied: surface water sources, groundwater sources, and rainwater is also a very important source because depend on the hydrological cycle, the complete hydrological cycle through this. If you talk about the Indian perspective, we'll be having four seasons. Like in monsoon seasons, 4 months we'll be having a rainfall in this because most of the water, fresh water. The rainwater is the most important source for the fresh water, right? So most of the cases we are totally dependent on the rainwater sources. And fourth one, that is water obtained from the reclamation activities. That is also important, but play a very less importance. Very less amount of water will come through the reclamation activities. But mostly we'll be having a surface and groundwater sources only. Water from the bell and galleries with the flow augmented from some other sources, charging basins, ditches, diffusion galleries, and wells will also fulfill this percentage. Water obtained from the desalination or reclamation activities will be desalination plants. Saline or brackish water may be rendered useful for drinking purpose by installing desalination plants at the ocean and all that. Very less percentage, as I told you. Distillation, reverse osmosis, electrodialysis, freezing, and solar evaporation plants, all kind of plants through this. If you are going to set up, of course, installation cost is very high for this. So through the desalination also, we will get the water. And reuse of treated wastewater, sometimes what will happen, this is also will come into the reclamation only. So if you treat this wastewater, sewage water, and once the sewage water is treated, it will be called as a treated effluent. And treated effluent, where you are going to use it? Either you are going to use it for the sewage farming, or you are going to use it for, or you are directly going to dispose it of in a fresh water body. It depends, right? because as I told you, natural purification methods, water will be automatically treated. But the condition are water should be treated at the effluent, right? So there is the influent untreated sewage water. At the effluent means the treated sewage water. When the water is treated, you can discharge either into the surface water bodies directly, or you can use it for the other purposes, right? So if you are using for the drinking, that is not acceptable, but for the other agriculture purpose and for the industrial purpose, you can use this treated sewage water. Okay. So effluent or treated wastewater can be treated suitably for use and artificial recharge of groundwater. That is also there. You can recharge your groundwater bodies through this treated sewage water. We'll be talking about the water supply system now. Only 10 students we have it. So what are the objective for the water supply system? So water treatment of public supply to ensure the good quality of good physical quality of the water. Water should be free from the unpleasant taste and odor. Water should be free from pathogens, bacteria, and viruses, and nothing detrimental to human health as well as the living planet. This is the main objective for treating the water only. I'm talking about the municipal water supply. So these are the main objectives, and the municipal water supply system consists of the following unit. One will be the collection work. There will be the surface water sources, river, lake, dam, from where water will be taking through the rising man and through the we can say the piping network and all that. So one is the collection work, where water will be stored in a dam or in a reservoir or in a lakes and river, and water is collecting through the conduits. That all in a collection, that is in from the intake to the respective water treatment plant, the whole pipe network, the whole system will be called as the intake network. And this intake network, there will be a lot of valves arrangements, a lot of pumping stations are also required, right? In the rising wind, sometimes we have to go against the gravity. Then all starting from the intake structure to the respective water treatment plant, there will be a lot of plant. Sometimes to the respective WTP, we call as a transmission main also. Okay, the whole arrangement that a collection work will be the intake only, and transmission will be the whole transmission band, where the huge amount of water will be coming through the conduits pipe for flow, channel flow, and all that. Okay. And the treatment work, where all the unit operations will be carried out, starting from the aeration and then pre-chlorination. Then we'll be having a primary sedimentation tank, clay deflocculator, coagulation, flocculation process will be completing there. And then there will be a filtration chamber, slow sand filtration and rapid sand filtration. After that, clear water will be coming to, and it will be stored into the clear water reservoir. Before that, we will be having a post chlorination chamber also. So once the water will be treated through the filtration plant, it should go for the post chlorination purpose to make the water disinfectant. So so if you want to disinfectant the water, you have to go for the post chlorination. As I told you, we will be having a pre chlorination, post chlorination, like this. So pre chlorination you have to do it after aeration, and post chlorination you have to do it after filtration. And then once the water is clear, once the water is treated completely, you have to store it in a clear water storage reservoir. And then the distribution network. Through you have to design the distribution network for the particular community, because you have to supply this water, treated water, for the community. Then that you have to design a distribution network, proper distribution network for the city and town or whatever the community wherever you are going to supply it. And there will be the overhead storage reservoir, and there will be a ground level storage reservoir where you are going to store this water. And you have to provide the water with the uniform pressure for the whole community, and you have to optimize the pressure also. And the supply should be continuous. And sometimes you are targeting for the 24 hours water supply. Sometimes only in India, if you see, the water supply is very intermediate, only for 1 and 2 hours in a day, or sometimes alternate in a day. We don't have a 24 hours water supply. So then distribution network and everything you will be designing. So if you see the complete water treatment plants, water supply system, starting from the collection and intake structure to the transmission main, through the transmission main to the treatment unit, where the unit operations like primary treatment and secondary treatment will be followed, including aeration, dechlorination, clariflocculation, where the coagulation and flocculation will happen, then filtration chamber, maybe there is a slow sand filtration and rapid sand filtration we are going, and then for after that there will be the post chlorination, where the chlorine will be added for making the water free from the pathogens and bacteria, and then you will be storing the water in a clear water reservoir, and then we are distributing it. This is a complete network that we are going to discuss it. Okay. So and then finally, fourth one is the storage and distribution, as we have already discussed all these things, right? That's you see what is the typical water supply system. We will be having a source of water, intake structure, and then you are going to treat it, you are going to storage it, and you are going to distribute it. Okay. So maybe the groundwater body, surface water bodies, involve water purchase if you are going to purchase the water also. So there are the various sources. Sometimes you can go for the combined also, surface come groundwater. So there will be the hand pumps and tube wells and well connections, including with the river and pond. Sometimes what will happen throughout the year, if the river is not perennial, if water is not available throughout the year, then you have to provide the pumping station. You have to extract the water from the ground also. So the combined type of intake structure also you can provide it. If I'm going for the basic processes for the treatment, there will be a primary screening, sedimentation, filtration, sand or gravel, chlorination chamber, where the post chlorination is followed. And then if water is very hard, you have to go for the water hardening process, the water softening process, and the hardness has to be removed from the water. And there will be some advanced arrangement also, that reverse osmosis and all we can achieve it. I have told about the storage reservoir. Maybe it is a OHSR, overhead storage reservoir. When you taking a water on a high height, for the whole community in a this is the complete water supply system. You see that is the source, primary storage near the WTP plant, then treatments where the various treatment unit operations will be followed, and there will be the clear water reservoir where water will be stored in a GLSR or in a clear water reservoir, and then water has to pump for the OHSR. This is an overhead storage reservoir. Yeah, we must see in your community. And through this, water has to supply through the distribution network. And this is the distribution network where the branch and submains pipelines you have to distribute it. You have to design it, and then you have to maintain various hydraulic parameters and flow rate and velocity and pressure. You have to maintain it constantly, like this. And there will be the line mains here. There will be the joining system, John 1, John 2, John 3, John 4. So first John water supply will be 6 to 7, and then another John 7 to 8. Like this, lineman will keep opening the valves there, so he can distribute the water supply. And starting from the source to the distribution, you have to design everything in a water supply and treatment engineering. Okay. This is the collection and conveyance of water supply systems. We'll be having a types of intakes. We'll have, according to the type of sources, we'll be having a river intake, canal intake, reservoir intake, lake intake. According to the position of the intake, we will be having submerged intake, exposed intake. According to the presence of water in the tower, we will be having wet intake towers, dry intake towers. And site selection of intake is also important. It depends on the following factors. Availability of water is it should be available in all the seasons, right? Quality and quantity of water should also check before before taking the water from this source. And this water body should be away from the pollution, and it should be nearer to the city, so the transmission cost should not be very high. So we can reduce the cost for transmission for the part network and all that. And upstream side of the rivers, you have to check it so the water can be flowed through the gravity most of the cases, and cost and reliability factor also play a very important. If it is a dam structure there, then cost and reliability factor also you have to check it, because most of the cases we will be going through the gravity mains pipelines. If we are going against the gravity pipelines, then intermediate pumping cost will be involved, so extra cost will be involved for the rising main as well as for the distribution pipeline. So there are the dams structure, various types of dams you have studied in your geotech and soil mechanics, I think. So we'll be having hydraulic structure constructed across a river to store water on its upstream side. There are some types of dams here: gravity dam, arc dam, buttress dam, steel dams, timber dams, earthfill and rockfill dams, right? These are the basic classifications that have been given. Classification according to the use: there is a storage dam, diversion dam, detention dam. And the common examples are gravity, rockfill dams, arc dams, well barrages. Classification according to the hydraulic design: we will be having overflow dam and non-overflow dams. So spillway and gravity mains will come into this category. There's a classification by material also. There's a right dam and non-rigid dam. So here the classification will be gravity, arc, buttress, steel and timber dams. Earth dams and rockfill dams will come into this category. And why the intake structure is required, why it is required, what is the requirement of the intake structure. The general, we'll be having two parameters here. The general requirement of an intake structure: first you have to check the structural stability, and number second is the hydraulic efficiency. So those two parameters play a very important role while you are choosing the intake structure. So, so no obstruction to navigation, no danger of floating bodies, noise trouble. These are the things that you have to take care. The water surface source that we have it, we have to check the things. There should not be no floating particles, and there should not be a debris, much debris on a river side, and there should not be a noise to the intake structure, what kind of intake structure that you have to build up, because you are storing a water somewhere on a surface water body source, that you have to build the structure, some intake structures there, and you have to check the various parameters, because you are building something inside the water body. So structural stability play a very important role. You have to check the shock waves and all that against the shock of the earthquakes. And hydraulical efficiency also you have to check it. There is a smooth entry into the water conductor systems to ensure gradual transformation of static head to conduct velocity so as to involve hydraulic losses. What are the functions of the intake? Intake structure serves to permit withdrawal of the water. So I'm starting from the intake. Then once the intake is over, we'll go for the transmission main. Then I will cover for the whole the treatment units. First, I will cover the water characteristics. I will go for the water quality analysis. Then I will go for the treatment, right? So just the treatment units. Then we'll go for the distribution. Or likewise, the whole WST will cover it. Then we'll go for the wastewater engineering. Okay. So intake is the first requirement for the water supply treatment structure. So that's why we are covering from there. So what are the functions of the intake? Intake structure serves to permit withdrawal of water in the reservoir over a predetermined range of reservoir level to outlet. And the other function serves by an intake are to support necessary auxiliary appurtenances such as trace rack, fish screens, and bypass devices, and etc. This is the simple submerged intakes. And there will be intake towers. There are the various structures. I will be coming in about the various structures. These are all the intake structures actually that you have to build up near the dam or near the surface water body. This is a simple submerged intake. This is the intake towers. There are the two types of falling. Two types we have it for the intake towers: wet intake towers and dry intake towers. that you have to build up near the dam. There's a river intake also. What kind of river intake you have to design it? You have to construct it there. There are two types here: twin well type of intake structure and single well type of intake structure. Okay. There's a some well here. There's a water, yeah, canal or lake, whatever. If it is a river also, because in the river, the structure you have to build up there only. The from the upper stream to lower stream side, so you can store the water and you can distribute it directly to the respective water treatment plant. Head loss, you have to check it. There is a head loss formula, that West-West formula, that Darcy-West-West formula, Hazen-William formula also you have to check it. I will be going for the one numerical part for the intake structure. And then slope also you have to check it, slope of the energy line. And pipe network, you have to check it, which pipe you are using it. So CH value for the cast iron pipe will be 130. So like this, if you are using a ZI pipe, if you are using UPVC, so depend what type of pipe you are using it. There's a bell mouth and press rake also. That also you have to construct it sometimes, because sometimes there is the overflow. You have to bypass this excess amount of water to the agriculture areas, or maybe in the low-lying areas, because dam should not be overfilled. Okay, if there is both the condition, if the excess amount of water is there, then extra storage is needed. If the very amount of water is very less, if we are not getting a sufficient head, that also you need some extra arrangement to fulfill that intermediate demand, right? So you want a constant water head throughout the year. So the water problem, if there is no water head, of course, and at the treatment unit we will not get the sufficient amount of quantity of water, so treatment process will disturb. We don't want that. There is a bell mouth and press racks structures. So the flow velocity through the outlet conduit is generally kept as 1.5 meter per second, and this helps to determining the area and diameter of the withdrawal conduits. And we'll be having irrigation intakes like press racks and supporting structures, bell mouth entrance with the transition, opening in rectangular circular openings, and gate slots, closing devices with air vents and trusses. There are various arrangement you have to make it there. A lot of gate openings and valves arrangement you have to make it. Suddenly you have to, generally they are using nowadays SCADA operated mechanism, so all the valve mechanism can be operated, and they can check how much discharge we are getting it, how much flow rate we are getting it, how much water head we are getting it, right? What is the total quantity of water is available in every month and every week, they can check it. This is the design procedure for the intake. So first you must understand about the content equation. Area of the skin, you can decide it. Discharge divided by velocity through the skin. Suppose if you are providing a 4-5 skins, then flow rate you have to distribute it equally. There is a, suppose we used to calculate water in MLD, million liter per day capacity. So if you are getting a water demand for suppose 5 MLD plant you are going to construct it, water treatment plant, and based on this you can divide the inlet. Okay, so suppose if you are going to provide generally in a water treatment plant, municipal water treatment plant, we don't go for the coarse and fine streams, but if you have to remove the debris and physical particles, then you can provide the streams, and likewise you can divide the flow rate. So there is a various standards for maintaining this. There is, as I told you, CPHU manuals, Central Public Health Environmental Engineering Organization CPHU manuals. So through that you will be getting all the details for designing this intake structure, and you can design it. There is some technical standards that you have to provide it. Height of the skin is found assuming to the bottom of the skin is to kept 0.15 meter above canal bed, and also considering the minimum water level in canal. Okay, we are not doing anything, only the simple formulas you are going to apply it. Length of the skin also you can get it area by height. Area you can suppose if it's a design conduit area, if you want to calculate it. So generally the velocity you are going to provide it 1 to 1.5 meter per second, and area you can get it through this, and then you can apply the Hazen-William formula for getting the head losses, and slope you can get it through this formula, this one. No? This is the Archive-Search formula. Through this you will get the head losses, and velocity you can get it through the Hazen-Williams formula. The slope you can calculate based on this head loss divided by the length of the conduit. So simple calculations you have to do it. So suppose this is an example. Design a bell mouth intake of a city of 70,000 persons, drawing water from a canal which runs only for 10 hours a day with a depth of 1.6 meter. Also calculate head loss in the intake conduits if the treatment plant is 0.5 kilometer away. Assume the average consumption per person is 160 LPCD. Assume the velocity through the screen and the bell mouth is 0.3 meter per second and 0.5 meter per second respectively. So first calculate the total water demand in milliliter per day, the water quantity. Total water quantity, so the population multiply with the respective water demand, how much they have given it, LPCD, 160 LPCD. So if you multiply with 160 LPCD, you will get it 11.2 million liter per day. So if you want to go for the conversion, so if they're converting in million liter, then you have to divide by 10 to the power 6, and then you can get the million liter per day. Okay, so that conversion you already know that. So 70,000 multiply with 160 divide by 24 into 60 into 60, so you will get it in a million liter per day. If you want to convert into liter per second or meter per second, then based on this you can make the conversions. So see here suppose since the canal only runs for the 10 hours a day, this whole day flow is required to be drained in 10 hours. So 1.12 into 10 to the power 6 meter cube per hour, you can convert it and divide by 10 to the power 3, then you will get the total capacity, total discharge flow 0.311 meter cube per second. And area of the screen, simple, discharge divided by velocity through the screen, you will get it 0.15 meter per second. Area of the course screen, you will get it 2.075 meters square finally. And these are the standard parameters. The top of the screen is kept minimum level, and these are the they have made considered as 1.15 meter, and the minimum length of the screen you can consider it. And then finally you will get the number of openings, 1.8 divided by 0.03. So there are 60 number of openings they are getting it. So number of bars 59 can be assumed, and the diameter of the bar 20 mm length occupied by the bar of 20 mm, you can provide it. So the total length of the screen 1.8 plus 1.18, so approximate 3 mm you can provide the length of the screen total. Head loss equation will be same. Hydraulic mean depth, I will come for the sewer network, then you can understand in a more detail. Hydraulic mean depth is nothing but area divided by the wetted parameters. So if it is circular conduits, so what is the area of the circular conduits divided by the wetted parameter, you will get it A by P for the hydraulic mean depth. This is the same equation as in Williams formula. Selection of pipe, you have to understand the various things. Durability you have to check, strength you have to check, hydraulic parameters, hydraulic efficiency you have to check it, and cost factor also you have to check it while you are going for the selection of the pipes, right? So as I told you, two things are there. One is the transmission main, another one is the distribution pipeline. In the distribution pipeline, we will be using a very small pipeline. In the transmission main, we will be using a bigger diameter, larger diameter pipelines. And there is a chances for the water hammer also, water hammering actions will take place there. What is water hammering? Once the water is flowing in the transmission main, because the supply of sometimes what will happen, we cannot be directly dependent on the gravity main systems, right? Sometimes there are a lot of pumping stations required in between to get the required flow. So if there is fluctuation in the electricity, and if there is a fluctuation in the demand also in night hours and day times, if the flow is not proper, so what will happen? The interior wall of the pipe, the hammering action will take place. The bumping sound will come out inside. If there is sudden breakdown happen in electricity, so the pumping station will stop. So the flow also will be disturbed inside. So what will happen? The water is having a huge amount of pressure energy. It will create a internal pressure on a pipe, right, in the vertical direction. So what will happen? There is a chances that pipe network can break it. The Suddenly the pipe network can damage, and suddenly all the valves connections, everything will fail, right? So we don't want any water hammers actions will take place inside the rising main. So for that you have to check the durability of the pipe network. The pipe network that we are going to use it should be strong enough to sustain the various things, right? So water hammer analysis that you have to do it before you are going for the rising main calculation and transmission main if you are going to design it. And then you have to check the material for the abrasion and resistance purpose, abrasion and corrosion purpose also you have to check it. The material that we are going to propose it should be abrasion free as well as the corrosion free. Okay. And the life design period you have to decide for the piping units also, maybe from the rising mains as well as from the distribution pipe network. Then design period you can decide it. I will come for the design period. So what are the factors that you have to take care while you're proposing pipe material for the rising main and distribution main? Strength and durability you have to check it. Capacity of the pipes you have to check it. And the corrosion and abrasion resistance you have to check it. And operation and maintenance cost also you have to check it. So there are in the market various range of pipes, various materials are available for the pipes. There's a cast iron pipes are quite common, wrought iron pipes, steel pipes, concrete pipes, cement line cast iron pipes, plastic or PVC pipes, asbestos cement pipes, copper and lead pipes, wooden pipes, petrified clay pipes, right? Cast iron pipes are joined together by means of balanced spigot and threaded and flange joints. So of course, as I told you, we'll be having a 20 to 30 meter pipe network, right? So so you have to interconnect the various pipes. So one pipe is having a maximum length, suppose 20 to 30 meter. Then you have to connect the another pipe. Then you have to join the pipes. So various appurtenances are required. You will be having a elbow, T-joints, right? And you have to make it leakage free, leakage proof. These all the connections. So and sometimes what will happen? You need a air releasing valve also. In between, you have to put the air releasing valve, right? So appurtenances as well as the pipe for the pipe material along with the appurtenances materials are also required. These are the water supply pipelines. We generally go for above on the ground. We used to put it, these big water pipelines. These are all the transmission main pipelines. Now we'll come for the water demand and quantity estimation. That is very important, water demand and quantity estimation. Okay, so we see the water demand and quantity. We'll be having a respective population. Suppose serving population is 1 lakh, and then you have to understand the design period for a particular structure. If I'm talking about the water treatment plant, if I'm talking about the transmission main, if I'm talking about the distribution main, all the pumping units. So all the components are having their design period that you have to understand it. Overall, suppose 30 years of 30 years you are providing for the water treatment plants, right, for various unit operations, 10 to 15 years for the pumping stations we are providing it design period. Till how much time the structure will remain, we can say stable. Of course, there will be operation and maintenance cost involved in that, but they will take the ideal period. So 10 to 15 years in this structure, nothing will happen. That is called as design period. Okay, that you have to consider it before designing for any structure. So water demand, you have to check it. How much, what are the rate of water supply you are going to supply for the city or for the town. So per capita, what is the supply? Per person, how much water will be consumed on a daily basis? That is called as water demand. So that you have to decide it. depend on various parameters. What are the living status, what kind of living status they have in the public, and what is the economy profile of a particular community, right? If the status is luxurious, of course they will be using more resources and the water demand will be high. So depend, water demand can vary, but uniformly you have to take the water demand for the small town as 135 LPCD. It keeps varying for the domestic. What there are the various types of water demand. We'll have domestic water demand. We'll having industrial water demand. We'll be having water for the commercial operations also. So commercial water demand we have it. We need a water for the firefighting actions. That also we have to reserve some water. We need a water for the floating population. The people will come for their business purposes in offices and they will come go back. That will be considered the floating population, right? And we need a water for what we called as commercial operations and all that, right? So there is the various types of water demand. Then the institutional demand also will take place, right? The water is required for running an institute for the daily uses and all that. If there's a hospitals and all that, right? Service sector, they need also water. The railway station, airports, there also water demand you have to decide it. So there are the various types because the uses of water, the capacity of water utilized by the particular purpose is different. If domestic purpose, if you take, daily water consumption will be different. If I'm going for the commercial purpose, water demand will be different. So you cannot provide the same water demand for all, right? So as per the WHO and even a CPHU, MOUD, Ministry of Urban Development has given the set of there's a manuals, water supply and treatment engineering manuals. Ministry of Urban Development, they used to reform those manuals, and there the standard because water demand is given. Okay, so generally what we do the calculations 135 LPCD we used to take it, right? Generally it will be given in the questions. Okay, you are going to supply the water on a demand of 135 LPCD, and the serving population is given. So what will be the total quantity of water that you have to treat that? Then you can estimate it. So design period, as I told you, 20 to 40 years for the water supply, you can take it. And there are the population forecasting methods, because wherever you are going to design a water supply system, you cannot design for the today's demand itself. So at least you have to design a water supply and treatment units for the intermediate years and for the ultimate years also. But the previously at least you have to design a water treatment units, your water treatment plant for the intermediate period. Suppose today is 2020, so next 2035. So after 15 years, right, what will be the total population? So population forecasting play a very important role for estimating the water demand and calculations. So you have to estimate the population, future population. Once you understand what is the future population for in 2025, based on this you can calculate the demand, know how much water will be needed for serving this population. So population forecasting methods, there are various methods available for getting the water demand calculations. So I'll be talking about all the methods and how to do that, how to use these formulas, and how to predict or forecast the population. Okay, and factors affecting the change of populations are because these are depending factors, depend on the living style of a country. What is the total GDP of a country? What is the growth rate we have it? And we have to check the from the census department. You have to check the previous year's data also. So last 50 years calculations, you have to check it. What is the city? It depends city to city and region to region. So suppose if I'm talking about the particular region, Bangalore. So Bangalore last at least 30 years data you have to check it for the population. How the population is increasing. What is the growth rate pattern? What is the total cumulative growth is happening in a population in last 50 years? Then based on this, you have to check what is the floating population there and how the population is increasing, whether it is exponential growth is happening, whether it is a linear growth is happening, whether the logarithmic growth is happening in a population. All those factors you have to check it, and it depends on various facilities also. What is the birth rate? What is the in a particular city, and what is the we can say the death rate in a city, how much the infant mortality rate, IMR also you have to check it, And you have to check the increase and decrease due to the migration population. People are going for and shifting from the city because of the job relocation, and they are getting better opportunity in another city, and they are shifting from the city. So you have to check the migrated population also, and these all things are all data, previous years data are available with the census department. You can collect it, and based on this you can you can forecast in a future, right? It's a planning stage actually. In the planning stage, there are the various options are available. You have to choose which option will be better for it. Okay. So there's a design period given. Storage by them, you can provide 50 years. Infiltration works 30 years. Pumping sets, all prime movers except electrical motors. So you can provide 30 years. Electric motors and pumps 15 years maximum. Water treatment units, you can provide a 15 years. Pipe connection to the several treatment units in small appurtenance is 30 years. Raw water and clear water conveyance 30 years. Clear water reservoir at the headworks, balancing tanks and service reservoir. Even an overhead reservoir and groundwater reservoir, you can provide maximum 15 years. The distribution system, you can provide a 30 years. So this is the data given by standard estimation from the water supply and treatment manual. That roughly you can provide that much of a period. So design period, once you decide a design period, you can go for the calculation for the how much water quantity is required and how much quantity of water need to be treated. And then population play an important role. So going for the population forecasting methods, there are the 9 methods available here. There is the arithmetic increase method. Second will be the geometrical increase method, incremental increase method, decreased rate of growth method, simple graphical method, graphical comparison method, master plan method, a joining method, and logistic curve method. Okay. So what is the basic principle for in all the methods? You have to find out the growth rate. Now growth rate can be constant or can be vary in every year. So based on this, you have to check the first the growth rate. What is the growth rate pattern with respect to time? So suppose here we have made one graph. This is x-axis and y-axis. In that respective time will be given in years. Suppose 1990, 1991, 92, 93 like this. This is the time given. And every year, what is the population growth? So based on this, if you mark population growth rate, if you want to calculate it, you can easily calculate it like this in every cross. So suppose I'm just framing the concept for the growth rate. Suppose if you are taking the A to B is the early growth, B to C is the exponential growth, a logarithmic growth you can take it, C to D you can take the constant growth, a straight line curve, and D to E is the late growth suppose. So slope of the curve will be dP by dt. So dP by dt anywhere you can take it. If it is a constant, it will remain constant throughout the every points. So suppose dP1 is equivalent to dP2 is equivalent to dP3 method. So in the constant growth curve method, the ratio will remain same. It will remain constant. And this arithmetic increase method, always the growth rate will remain constant. The linearly graph will work with respect to time and population. So dP by dt will remain constant here. This method is applicable for the old and settled cities. Okay, so per decade increase in population is assumed to be constant in population forecasting by using arithmetic increase method. Here I have tried to explain here. There's a population increasing and then the saturation comes. These things. Now here dP1, dP2, dP3, dP4 population in a respective year. Suppose 1991 that much population, then 1992 this much. Like this straight line curve you will be getting. And anywhere you can find a slope, it will remain same. Okay. So this is the dP by dt curve we called as. So you can how to derive this formula for it. So there is a present population P0. You can take it as a present population. So above you can take all the positive population P1, P2, P3. Sorry, P1, P2, P3, and down also you can take the P2, P2, P1, P2, and P3 like this. So these are the previous years. These are the future years. Okay, then this is the present year. Present, future, and past. So like this, suppose if you are having a last 10 years data, you can put all the down, and then if you want to forecast the population for 2030, whatever the population 2021, 22, 23 like this, you can and predict or forecast the population based on this arithmetic increase method. Now, what is the formula for it? As I told you, per decade increase in population is assumed to be constant in population. Let's suppose P naught will be the latest non-population for the last decade population, and X bar, I have put it X bar, you can put it on the top, X bar be the arithmetic average of per decade increase in population. And population after 1 decade will be P1 is equal to P naught plus 1 into X bar. Then population after 2 decades, like this, you can go for it, P1 plus X bar. Then you can write it in terms of P naught plus 2 into X bar. And arithmetic increase, arithmetic average means what? The total sum of the growth rate divided by the number, total number. So you can get it. The population after n decade, the final formula will be Pn is equal to P naught plus n into X bar. As I told you, this method is quite suitable for the old cities and large cities with the the considerable development. If it is used for the small, average and comparatively new cities, it will give low result than the actual values. Actually, what you have to, I will talk later about this. In this method, the average increase in the population per decade is calculated from the past census report. And this increase is added to the present population to find out the population of the next decade. Thus, it is assumed that the population is increased at a constant rate. So dP by dt is the constant here, or rate of change of population with respect to time will remain constant. The second is the geometrical increase method, ZIM. Here the percentage increase in population from decade to decade is assumed to be remain constant. Geometrical mean increase is used to find out the future increment in population. In the formula you can derive it. The population at the end of the nth decade, the Pn will be P naught into 1 plus Iz by 100 to the power n. Iz is the geometrical mean. I will tell how to calculate the geometrical mean. P will be the present population, n will be the number of decades. Suppose today is 2020. So if you want to calculate the population for the census itself, so 2030 if you want to calculate, so you will put a P 2030, P 2020 into 1 plus Iz by 100 to the power whole to the n means 1 decade is it, so 1. So like this, every decades you can calculate the population. Suppose if it is a 1 decade, if you want to go, so what will the population in 2020? Suppose 2000 after 2030, what will be the population? 1 decade means 10 years, like this. So you can derive this formula. Then if you want to go for P2, the next decade means 2 decades means n will be equal to 2, and growth rate you have to calculate it. Similarly to compound interest, like the growth rate will be similar to the compound interest here. There's the compound interest, there will be principal amount, interest rate, and time is given. Then compound interest you can calculate it. No, the same way you have to calculate it here also, growth rate. So percentage increase never remain constant. Percentage decrease when the growth of the city reaches to the saturation level. So you can check the growth rate here. The predicted population, forecasted population divided by the present population, okay, to the power 1 upon n minus 1. This is a saturation level population. And geometrical mean you can calculate in such a manner. Maybe the growth rate, there are the two methods here. In most of the cases you have to go in this method only, because CPHU manuals recommend this method. The multiplication for all the growth rates, it will go up to n to the power 1 by n will give the Iz value, the Iz this one. Okay, so multiplication for all the values you can go it. R is the increase in population divided by the original population for each decade. So about 2031, 2040, like this you can calculate it. And you have to check the previous growth rate also. 2010 growth rate, 2000 growth rate, and 1990 growth rate, and based on this you can get the better approximation for the future. You have to check the close results actually. What will be the population in 2020 and what you have predicted when you were in 2010. If it is approximation is coming very near to the real values, because every 10 years they are going to go for the census calculation, census estimation, right? They count the population. So if the result is coming quite closer for the approximation, then you can take this method. So you can choose based on this which method is most reliable for the particular purpose. So this method gives the higher values, hence would be applied for a new industrial towns at the beginning of the development for the new for only few decades. So you can choose it based on, it's a planning stage actually. The town planner or as an engineer, you have to decide it, which method you can apply for a particular city. There's an example given here. The following data have been noted from the census. There will be year census wise 1940, 1950, 1960, 1970, calculate the probable population in the 1980, 1919, 2000. Okay. So next 3 decades population you have to check it, you have to estimate it. So you can write the year population, increase in population, this much blank, and then what is the difference, 8,000 to 12,000, 4,000, what is the difference, 17,000 to 12,000, you can write 5,000, like this you can write the differences, increase in population. Now percentage increase in population you can calculate it, initial population, the difference, how much you are getting it, 4,000 divided by the present population 1940s. So 4,000 divided by 8,000 multiplied with 100. So percentage increase in population you can get it, basic formula, basic understanding, 5,000 divided by 12,000, previous population multiply with gap divided by previous population multiply with 100, gap divided by previous population multiply with 100. So you will get here percentage increase in population 50%, 41%, and 32.7%. If this is the arithmetic increase method, this should be constant. But here there is a percentage increase of population is not constant in a geometrical increase method. It keeps varying here. Average per decade you can calculate it 1, 2, 3. So for the 3 decades you can calculate it. You are getting the sum of this 124.1 divided by 3. You will get this much number 41.37. And the population at the end of the various decades you can calculate it now. 1980s, 1970 population 22,500, that is 22,500, and then you can apply this formula. Same formula and you can get the result. So P naught plus 41.37 divided by 100 percentage it is, multiply with the present 1970s population, and you will get this number. Now you have to check in 1980s if you are getting that most approximation exact value, not exact, but it is the graph is coming very near, then you can choose this method, geometrical increase method. In 1990s also you can calculate it, 2000 also you can calculate it in such a manner. That is the incremental increase method. It combines both actually, arithmetic increase method as well as geometrical increase method. While adopting this method, the increase in incremental is considered for calculating future populations. The incremental increase is determined for each decade from the past population, and the average value is added to the present population along with the average rate of increase. This line is very important, and the population after the nth decade will be this one. As I told you, this is a combination of 2 methods, arithmetic increase method and geometrical increase method. So here to here there will be the AIM method, and here onwards it will be the GIM method. So both are combined here. So Pn, the formula will be P plus Nx plus, you can put Nx bar also, N into N plus 1 by 2 multiplied with Y. Pn is the population after the nth decade. X will be the average increase per decade. Y will be the average incremental increase. So average increase plus average incremental increase per decade all together will give the combined value. So this method is most precise and mostly accurate. So generally mostly prefer method, but in Indian conditions. But again, you have to check the lot of topographical conditions, lot of what is the population pattern for the last year for the particular city. Lot of factors you have to check it. Okay, before proposing this. But while you're proposing a population forecasting, you have to check all the methods and you have to check the previous calculations, previous exact numbers, and then based on this you can decide which formula will be best for the population forecasting. So we have explained this method. increase in population they have calculated differences. Then incremental increase on the increase again they have calculated. Average they have calculated, and every year they are going to calculate 1980s, 1990s, and 2000. This is the logistic curve method. Logistic curve method, you have to plot a curve between time and population. This curve will be like this. There the saturation value of the population. After the population will not increase. And then if you see this curve, there's a dp by dt here to here. dp by dt is directly proportional to p. And if you see here, this portion, dp by dt will follow the straight line curve most of the cases, and that's why dp by dt is remain constant. And here m to n, dp by dt is directly proportional to ps minus p. ps is the saturated population and p that is given population. So this curve will be divided into three parts: jk, kl, and mn. jk, kl, lm, and mn. So the early growth of the city is shown by the curve jk at an increasing rate of depth. dp by dt is directly proportional to the same thing I have explained it. K to m will remain constant, and the transitional curve km also passes through the point of inflection. L will be the point of inflection. The sudden changes will happen after that. And later on, the growth from m to n follows the decreasing rate. So there is no constant rate of changes happening in a population for a particular city. Then you have to go for the logistic curve method. So variation are quite high. Sometimes it will become very constant. Sometimes the growth rate will increase. Sometimes it will decrease. Then if there is a fluctuations happening in during the previous year, 30 years data, every census the population estimation is changing. If you compare with the exact number, then you have to go for the logistic curve method. Quite suggestible for it. Then dpa by dt is directly proportional to ps minus p difference. P is the population of the town at point T from the origin Z, and PS is the saturation value of the population, and the S shape curve. This curve is called as S shape curve. So logistic curve values will come through the S curves. This curve is called as the S curve actually sometimes. It's called as a logistic curve. So this method is used when the growth rate of population due to birth, death, and migrations takes place under normal situations, and it is not subjected to any extraordinary changes like epidemic, war, earthquake, and any natural disaster. Okay, so for the normality you can propose this. There are some calculations given here by using this equation. They made it. So the population follow the growth curves, characteristics of living things within limited space and economy opportunities. If the population of the city is plotted with respect to time, the curve so obtained under normal conditions look like a S-shaped curve. That's why we call it as logistic curve. So this is a scientist, Bernhulst, after long research work, has given the following mathematical solution of the logistic curve. So MC Lin further suggested that if three pairs of the characteristics values P0, P1, and P2 at the time T0, T1, and T3, which are extending over the useful range of population, are so chosen that T0 is equal to 0, T1 and T2 equal to twice of the T1, the saturation values, PS, and the constant M and N can be determined from the above equation. So if you see this curve, this is the time, this is the population, this is the dB by dt, P and PS is given. So here what they are telling it, they are considering a 3 times T0, T1 and T2, and respective populations 3 pairs P0, P1 and P2. This is the extended version of Nest has given it. Okay, so he is going to calculate it log exponential PS minus P upon P minus log exponential, that is PS minus P0 upon P0 or P0, you can write it and then you can solve it. So finally you will get this number P, which is the required equation of the liquid logistic curve. So derivation, in order to derive it, first you must remind this number how to do that. Sometimes they will ask one number question or two marks question on that. So directly population they want to calculate it. So you put the given number Px, M will be given there, N or T you can find out it by using this, and then you can get the number. So they will be asking what is the required population in this census, this decade, and directly calculated from the logistic curve method. And then if you further solve it, M will be Px minus P naught upon P naught. You can solve in this. You have to remind it actually, it's a little bit, you have to remind these numbers. Only one thing they can ask it, small numbers they can ask it. Suppose in this question they have given it, the population is given, P naught is given 35,000, P1 is given 78,000, P2 is given 1,15,000, T naught, T1 and T2 everything is given. Then PS directly you can calculate it. Price of the P naught into P1 into P2 minus P1 per square into P naught plus P2. Generally in a GATE they will not ask a question which is in which you have to remind a big equation and all that. Okay, they just keep checking the concept. Any one thing they can ask. M values they can ask if they have given a present population, everything. They can ask one value, right? Small things. Then sometimes they can ask this N value also. If all the numbers are given, you can get the number of N value. There's a chances PS also they can ask. So if you know the P naught is given, P1 is given, P2 is given, then based on this you can get put this equation and get the number. Whole problems they will not ask. Very small iteration they will ask. And there is a master plan method or joining method also for the newly proposed cities. For the master plan cities, you can propose this method. If there are any future expansion of the cities going on, then you can go for this method. Okay. The development of town and cities is not allowed in haphazard manner. So it's a very well planned cities. If you in India, if you see the Chandigarh, right now, if you see the Amravati, they are going to plan it the whole cities following the master planning schedules, and they are making a smart city concept based things. They are making it. So for this master planning or joining methods will be very good for it. It's a very systematic plan for it. There's a decrease rate of growth also. What will happen? The rate of growth will decrease with respect to time here. The population rate of growth will decrease with respect to time, right? So here it has been seen that all life grow within limited space. If the complete growth of a very old city is plotted, it will be seen that the curve has S shape, which indicates that early growth takes place at an increasing rate. Later growth is at a decreasing rate, which indicates the saturation limit is reached. If you see this curve here increasing, then will remain constant, and then again directly dependent with the differences. So and then the saturation, after saturation decreasing of population, we can say the growth rate will happen. So for this you can go for the decreasing rate method. In this method, the average decrease in the percentage increase is worked out and is then subtracted from the last percentage increase for each successive decade. I will be going for the numerical, then you will understand how to apply this method. Then there is a simple graphical method. In this method, the population of the last few decades are correctly plotted to a suitable scale on the graph with respect to the decades, and the curve is smoothly extended to the future forecasting population, and the graph of present city is plotted from the beginning, and it will show the growth curve. So the typical growth curve of a city, that example they have given it. So nothing, what you have doing past year census data you are having it decade wise, you're going to put it time on x-axis, population on y-axis, and what you have to check it, various cross points, and slope you have to calculate every time, and you can, based on this, you can calculate the future population. So every time you will be getting a growth rate, here also growth rate, here also growth rate, here also growth rate, like this you are getting it, and then you can constant your result for the future population also. Typical city growth rate, you can get it. Because as I told you, these are all the approximation and probability. Exact numbers cannot happen, but at least we will be very close for the real result. This is the example for the decrease rate of growth method. We see once simple mathematical calculations. There's a year given, population given. First you have to check the increase, how much increase is happening in population. Then percentage increase in population, you have to calculate it. Then you see that 50 to ये 41.7 हो गया, then 41 to 32.7 हो गया. Means it is decreasing here. So this difference, decreasing difference, you have to write it here. Decrease in the percentage increase, you can write it here. And then here also 41.7 and 32.7, that also you have to write it. And then you can sum up this 17.6. And then average you can calculate it. Divide by 2. 17.6 divided by 2. Like this you will get it. And this also, sum of all the increase values, 14,500. And then how many number? 1, 2, 3, and 4. And then no, 3 only, 1, 2, 3 only, and divide by 3 if you do it, 4,833 it will come at. Now you have to forecast the population for 1980s, 1990s and 2000. So net percentage increase in population, 1980s. This is 1970, 1970 is given 32.4. And what is the growth, the percentage decrease rate here? 8.8. So 32.4. These are all in percentage. Here also are all in percentage. So they can ask any one number, right? In the GATE exam, they can ask only one question here. Okay, what is the population in 1980 by using a decrease rate of growth method? Any one concept for the concept checking, right? Not a whole question. So you have to calculate that. If you minus from 8.8, then 23.6 you will get it. And then you can apply this formula and then you can get the answer. So 22,500 plus 23.6, that number, divide by 100, multiply this to 22,500. The IAM method, the same method they are applying here, and then you can get the number. Only the calculation you have to put it in graph. Remaining things will remain same. This is another example for the decrease rate of growth method. So they keep asking in this, that's why I have put up two numericals. Same thing they are doing it. Increasing population they are calculating it. Then percentage increase in population they are calculating it. Then decrease in the percentage increase, how much it is happening. So if it is increase, you have to write in minus. If it is decrease, you have to write it in plus. Remember that. So this is all numbers are in percentage. Calculate the average for this, and then you can calculate the population 1990s, 2000, 2010. Population you can forecast it. So like this, the whole 10 methods, you have to forecast the population first, and then you have to choose the best method based on the availability, based on the constant data that has been given, and based on the previous data available also. Now we'll come for the water demands. Indian concerns, the domestic water demand you generally calculate as 50 to 60% minimum. So 135 LPCD to 250 LPCD you can take it, general iterations. So generally they are taking for the small town 135 LPCD. For the metro city you can take a 200 or 250 LPCD. It will be given in a question generally. Industrial demand, water demand will be 50 LPCD. Institutional and commercial water demand will be 20 LPCD. Fire demand, you can take it 10 to 15% of the total water supply. Okay, 10% water demand you can put it for the fire. Okay, if accidental fires happens, this 10 to 15% water should be reserved for this purpose only. Public demand, 10 LPCD. Demand to compensate losses in theft, 15 to 20% losses are acceptable. So 55 LPCD you can give it for this demand for the theft and losses. So fire demand, empirical formulas. There are some empirical formulas for fire demand. If you have studied the water supply and treatment engineering, you must know all those things, all the formulas. The recommended formulas, this one is a very recommended formula. So they used to is a wide use we are having it. Here some conditions are given. Population you have to take it in thousand always. Okay, so there's one formula as per the government of India. The fire demand will be 100 into population in thousands under root unit will be in into k into I. Custodian formula, and again the population will be given in thousand. So Q is equal to amount of water required in liter per minute. Population will be in 1,000. Freeman also, population will be given in 1,000. You will get the quantity in liter per second. National Board of Fire under writer's formula. This is a quite common formula that we are going to use it. Where population is less than 2 lakh, you can go for this formula. Again, population will be given 1,000 and Q will be liter per second. If the population is greater than 2 lakh, then you can take it Q as 54,600 liter per minute for first fire. Because sometimes what will happen in summer season, 2 times and 3 times fire occur, right? So one time if 15% demand you have consumed it, next time what will happen? So like this approximation 3 to 4 times you have to reserve the water for the entire year. Okay. Those are the various formulas. Per capita demand, you already know that how to calculate it. There's a total yearly water requirement of the city in liter, divide by 365 in a year, multiply with the design population. So you can calculate the per capita demand based on this. So generally, based on this, if we are generally calculating per capita demand as 135 LPCD to 250 LPCD. If you want to calculate it, you can calculate it based on this formula. So what is the total year water requirement of a city in liter and divide by 365 days, multiply with the design population. Kitna design population hai? If you have a 2 lakh population, multiply with 2 lakh. If you have a total yearly water requirement for 2 lakh liters, actually suppose 20 lakh liter, if you say 20 lakh divide by 365, multiply with 2 lakh population, you will get the desired per capita demand in LPCD, liter per capita per day, LPCD. Okay. These are the variation in rate of water demands. The maximum daily demand MDD draft, you can take it as 180% of the average daily demand. First, you have to calculate the average daily demand. Once you calculate the average daily demand, you have to multiply with 1.8. This is the peak factor actually. 1.8 is the peak factor here. What is Q max? What is Q average? Will give the peak factor actually. So Q max divided by Q average will give the 1.8 value. That is the peaking factor. So maximum daily draft, you can take it 180% of the average daily draft. If it is an hourly basis, then maximum hourly demand, you can take it 1.5 times, or we can say the 150% of average demand hourly of maximum day. Okay. If it is a maximum hourly demand or peak demand, if you want to calculate, it should be 270% of average hourly demand. So maximum daily demand, first one, maximum daily demand divided by average daily demand, you will get a 180%. Yeah, 1.8 is the peak factor for it. So maximum weekly demand divided by average weekly demand, if you want to calculate, it should be a 1.48 peak factor. Yeah, 148%. It roughly take a 150 only. Okay. Maximum monthly demand, if you want to calculate, the maximum monthly demand is equal to 128% of average monthly demand. These are the factors affecting the rate of water supply. Of course, the size and shape of community. These are the standard iterations. So if you know the peak factor, you can get the value. So these are the factors, affecting factors: rate of water supply, size and shape of the community, standard of living, climatic conditions, quality of water required, what is the quality of water, pressure in the supply, system of supply, sewerage, metering and watering rates, water meters rates, age of community in lawn and sprinkling. These are the affecting factor of the rate of water supply. How you are using it, how much percentage you are using it, it depends, right? And what is the pressure of supply, what is the hours of supply, if it is a 24-hour supply, if it is an intermediate supply, if it is a supply early in the morning, only in the nights, only the peak hours in the morning and peak hours in the evening, it is the water supply is happening. So depends, right? Generally, early in the morning, 6 o'clock to 8 o'clock or 9 o'clock, you can take the peak hours of water supply, where the water consumption is high. And evening, 4 o'clock to 8 o'clock, you can take the 4 o'clock to, not 4 o'clock, 6 o'clock evening to 10 o'clock, you can take the peak consumption of water supply, where the maximum amount of water will be used in kitchen and drinking, and making food and everything, right? In washing, bathing, and all that. So it depends. And quality of water also play a very important role. Based on the quality only, you will suggest the treatment units, right? So if the quality is worse, then more treatment is required. Of course, the installation, machinery cost, pumping cost, everything will be high. So we have to. That's why quality parameters is very important. I will move for the quality parameter once I finish this portion, and the metering rates also. What are the charges? Watering charges monthly basis. What are the how much charges you are the communities or the municipal corporation is putting for the water charges per 1,000 liter, how much charges we have to give it, right? The consumption, because the service sector, of course, some charges has to give to the municipality for running and maintenance operation. So that metering and charges are also applicable, depend. If it is very high charges, if you are putting it, the people will be kind of confused, so they will be using less water, because of course the water will be high then, like electricity bills, right? So how to calculate the Q average? The average water demand, daily per capita consumption. The same iterations, you can use it here. Q average will be the quantity of water supplied during the year by the number of days in a year and the number of persons served, percentage of annual average daily consumption. Percentage of annual average daily consumption, I'm taking as AAD. Okay, so here you can calculate a maximum seasonal consumption. Daily rate of demand will be the 130% of the annual average rate demand. Maximum monthly consumption will be 140% of annual average daily consumption. Maximum daily consumption, see, seasonal annually, daily, then monthly, then hourly, like this you have to check all those things. So generally it is constant parameters. So maximum seasonal consumption, if you want to calculate for the daily basis, it should be the 130% of annual average demand daily. If we want to go for monthly, then 140% of annual average daily consumption. The maximum daily 180%, maximum hourly consumption 150% of average for the day. Generally, you always design a water supply for the peak hours conditions, right? Maximum daily consumption basis, you have to design the unit operations. Effect of variation in consumption on design. What are the effects? Variation will happen in the consumption. What are the factors in design that you have to consider it? The filters in pumps. Pumps play a very important role, because most of the costs related to pumping stations only. In filtration chambers and filtration units also, that's maybe a slow sand filtration, rapid sand filtration, that also play a very important role. Distribution band, as I told you, 10 to 15% losses are acceptable. If the losses are coming 40 to 50%, then the major amount of fresh water will be wasted actually. So we don't want that. So the consumption rate will also vary based on how much percentage of losses are there, what kind of pipe network you are going to use it. If there are more leakages, of course the amount of treated water will be less, right, at the consumer end. And sedimentation tank and water reservoir capacity also vary. That also we have to check it. So generally, the annual average consumption should be 150 liter per capita per day for a given city, and maximum daily rate of consumption should be 180% of average annual consumption. So 1.8 K will be the peaking factor for it. Absolute maximum hourly demand. So 150 divided by 24, multiply with 1.3 or 130%, multiply with 1.4, multiply with 1.80, multiply with 1.50. So altogether, if you accumulate all the peak factors, multiply with, then you will get this hourly basis per liter demand. 30.7 liter per hour demand, you will get it. In various unit, if I'm talking about the filters and pumps, the filter units as well as the pumping units are designed for 1.5 times, 150% is, you can take it, times of the average daily demand. Always, while if I'm talking about the filters and pumps, it will be always designed for 1.5 times to the average daily demand. You have to calculate the average daily demand, and if you multiply with 1.5 factor, based on this, the quantity you have to decide for the filters and pumps. Suppose the population is given a 50,000, annual average consumption is given 150 LPCD. Filter unit should be designed as population multiplied with 1.5. This is 75,000 liter capacity. You have to design a filter unit for the 75,000 liter capacity. Okay. And what is the consumption total for the 50,000 population? 50,000 multiplied with 150. Yeah. And pumps should be designed as 75,000 liter of water in 24 hours. Like what will happen? The pumps will not run for 24 hours. Suppose the one pump is running for 12 hours, then discharge will be 75,000 divided by 12. So 6250 liters per hour discharge rate you can calculate hourly basis. Daily basis, if the pump is running for 24 hours, then it will be 75 liter water will be discharged in 24 hours. But if the pump is running for 10 hours, 6 hours, 12 hours, it will be given in a question. So based on this, you can divide the hours and you can calculate the discharge rate for the particular unit, liter per hours unit. Suppose distribution means the filters and pumps ho gaya. Now the distribution means are designed for the maximum hourly demand for the maximum day. So maximum hourly demand means 180% multiply with 1.8 multiply with 1.5 here. 2.7 multiplication factor should be considered for it. So distribution means will be designed for maximum hourly basis, because first you have to check the maximum daily demand, then you have to go for the maximum hourly demand. As I told you here maximum hourly basis you have to calculate it. So we have taken a 2.7 average factor here. 2.7 multiplied with average hourly demand. So directly you can write it here. I have put it at 2.7 here. So multiplication factor should be the picking factor should be 2.7 for the distribution demand. So if you are having average daily demand multiply with 2.7, then you will get the distribution demand, how much water is required for the distribution demand. Sedimentation tank and water reservoir are designed for average daily rate of consumption. So these average daily consumption, okay. Then we'll come for the quality aspects of water. The quality of water. As I told you, we were talking about the three parameters: physical parameters, chemical parameters, and biological parameters, biological characteristics of water. So before going for the treatment plant, you have to ensure the quality of water first. Right? Once you understand the quality, once you understand the impurity and pollutant available in the water, then you can suggest the respective treatment. Right? So typically we'll be having three kind of parameters: physical impurities, physical characteristics, chemical characteristics, and biological characteristics. And what is the objective for doing this? Because you have to fulfill the first objective. What is that? To ensure the water of good physical quality. Water should be free from unpleasant taste and odor, free from the pathogens. It should not harm the human being as well as the other living organisms, and containing nothing which might be detrimental to the health. Okay, it is so if you see the potable water and drinking water standard definition, so all the parameters you have to check it. Requirement of water for the domestic use. You see that in this definition everything will be considered. The water should be free from solids in suspension, no sediment deposit. It should be good in taste, free from colors and odor, free from disease-producing bacteria. There are some useful bacteria and unuseful bacteria, right? So that's why they are telling the free from the disease-producing bacteria, free from objectionable dissolved gases, sufficient quantity of dissolved oxygen, free from harmful salt, free from objectionable minerals, iron, magnesium, lead, arsenic, and other poisonous metals, and free from phenolic compounds like chloride, fluorides, iodine, should not lead to scale formation and non-corrosive. If you see from the environmental engineering point of view, what is the definition for a drinking water? So these are all the things should not be there in a water, and water should be colorless, of course. Okay. And this is the prime objective for treating the water actually. Okay. So that's why the quality aspect of water is very important, and how you examine the quality aspect of a water, that is very important. Okay. So whatever the terms we have used it one by one, I will go it. There are some physical parameters involved here. There are some chemical parameters. There are some biological parameters here. Okay. So that I will do it, and then I will go in one by one. So the quality of water testing, there is the objective to know the extent the impurity presence in a water. Based on this method, the degree of treatment is decided. As I told you, based on the quality aspects only, you can, once you have a water quality analysis report, you can understand and you can suggest what treatment is required for removing this particular type of pollutant, right? And then to ensure the quality of treated water before the public supply, there's the two objectives that we have to fulfill through the quality of water. Okay. Now, what are the impurities we have in water? There are the various based on this we have to decide. Suppose based on the size of the impurities, we have to decide. We are talking about the impurities. Now, what kind of impurities are available in the water? So based on the size of impurities, if you talk, there will be the micro size available, maybe the suspended impurities, the impurities which are in suspension form, the size of these suspended solids, your suspended impurities will be 10 to the power minus 1 to 10 to the minus 3 mm. We can say the 100 microns to 1 micrometer. Colloidal impurities, which cannot be visible, 10 to the minus 3 to 10 to the minus 6 mm, 1 micron to 10 to the minus 3 micron, more smaller particles. Dissolved impurities, 10 to the minus 6 to 10 to the minus 8 mm. Yeah, you can say 10 to the minus 3 to 10 to the minus 5 micron. So these are the, based on the size, you can define the impurities. And based on the nature of the impurities, there will be the organic impurities, there will be the inorganic impurities. What is the organic impurities? Organic matter which will promote the growth of organic matter, growth of microbes and bacteria. If the living parasites, pathogens, bacteria, viruses can survive and they can consume the oxygen and nutrient from it, it will be called as the organic matter. So these are some organic impurities as well as the inorganic impurities. Based on the size, we will be having micro and various size. Based on the we have a size in micron and mm. So based on the particle size, you can understand that. And based on the nature, there will be organic and inorganic impurities. If I'm talking about the inorganic impurities, all the nutrients. Suppose natural origins are harmless, but that included by humans are that there are two types of metals here, two types of alloys. One is the man-made and there is natural metals that we are having it. If there is a carcinogenic metals, carcinogenic components, like if we are talking about the cadmium is present in the water, chromium is there, nickel is there, zinc is there, lead, Hg, these are all coming under the inorganic substances and inorganic matter, right? So if I'm talking about suspended solids causes a turbidity in water. Dissolved impurities, larger in sizes, but not visible. Since water is good solvent, causes bad taste, hardness, and alkalinity. So I will come for the chemical characteristics and biological characteristics. Then I will talk in detail about it. There are some colloidal impurities. Colloidal impurities are electrically charged, very small in size, remain in constant in motion, not settled. So I will be talking about suspended solid, I will be talking about total dissolved solids, I will be talking about colloidal solids, right, colloidal impurities, and you must understand the basic definition about the between the suspended solids as well as the colloidal solids and dissolved solids, right? So colloidal solid is never settled. It will be in a colloidal form, very small in size. You cannot see that, and electrically charged, negatively charged particles these are. So if until unless you will not do some chemical treatment, if you not go for if you're not going for any chemical addition like a coagulant add, you just add it like a alum and all that. Then once the chemical reaction will not take place, it will not, these impurities will not settle down. Okay. Effect of impurities in water. Suspended solids. Constituents are bacteria, algae, protozoa, and silts. Some causes diseases, produce odor, color, and turbidity in water. These suspended solids. Dissolved solids. Salts, calcium and magnesium, carbonate and bicarbonate, sulfates and fluorides. Causes alkalinity, hardness. Hardness, I will talk about the hardness, about the temporary and the permanent hardness later. And it creates a corrosion also. Carbonate hardness and bicarbonate hardness comes because of the dissolved solid. There are sodium, magnesium, calcium, and chloride present in the water. Okay. Metals, metals and compounds. Iron oxide, manganese, lead, arsenic, barium, cadmium, cyanide, all impurities. These are the inorganic impurities will be present in the water. So you have to check the constituents. Poisonous, lead, cadmium, cyanide, all poisonous in nature. And if water is consumed, if it is having a cyanide and cadmium, it will create a problem for the human being, even any living organism. Okay. Effects will be taste and red color, hardness and corrosive, and even death can happen for the water animals because of the toxicity. Silver is also there. It creates a discoloration of the skins. Boron is also present, affect the nervous system. So there are the various constituents, organic and inorganic matter, some impurities, which creates a lot of problem for the health, and it is not advisable. Not even a health, it creates a problem for the corrosion, it creates a problem for the if I'm talking about the cyanide, it's a fatal death can happen, toxic illnesses, toxic and poisonous, a lot of impurities, a lot of disadvantage we are having it. Even the waterborne diseases, right? Most of the deaths happen because of the waterborne diseases. That's why we want a pure water. So these are the water quality parameters. I'll be talking about the physical parameters of water quality assessment, in which color, odor, turbidity, temperature, and conductivity will come. If I'm talking about the chemical characteristics, the chemical parameters of water quality assessment, pH, acidity, alkalinity, hardness, solid harmful chemicals, chlorides, sulfates, iron, nitrates, heavy metals will come in that category. And if I'm talking about the bacteriological parameters, we can say the biological characteristics of water, in which you can say the dissolved oxygen, biochemical oxygen demand, chemical oxygen demand, coliform, fecal coliforms. These are all the bacteria and viruses and pathogens available. And testing, you have to test how much bacteria and viruses are available in the water, and how to test it. There are some methods. So if there is any bacterial pathogens growths are happening, maybe they are increasing in their number, growth is happening in their reproduction, so that you have to check it. If there is any biological growth is happening inside, then you have to check the biological characteristics. So dissolved oxygen play a very important role for biological activities flourishing, right? Biochemical oxygen demand also play a very important role. So you have to understand all the parameters, and you have to check the BOD, you have to check the DO, you have to check the chemical oxygen demand, COD also. You have to check how many bacteria and viruses are available present in our water, right? Quantity you have to estimate it first, And first you have to check whether the bacteria or viruses are present or not. Then one test you have to do it. Once you understand whether it is present, now what is the quantity? What is the percentage? How many bacteria and viruses are available in that much of volume of water? Suppose 100 ml water, how many bacteria and viruses are present? So two tests you have to do it. First you have to for identification whether the bacteria and viruses are available, and second how many quantity of viruses and bacteria are available in 100 ml of sample. So these are the various things, and pathogens and viruses you have to test it in biological parameters or biological characteristics. So physical characteristics, as I told you, test order, turbidity, temperature, order. I will talk in one by one manner. Chemical, as I told you, total solids, chlorides, hardness, pH value, metals, dissolved gases, nitrogen, all that. And biological characteristics, coliform, microorganism, pathogen test that you have to do it. Bacteriological parameters. And I will start from the temperature first. So it's physical characteristics. The standard range for temperature should be 10 degree to 20 degrees Celsius. Warm temperatures are good for microbial growth. Solubility of gases depend on temperature. If there is more temperature, dissolved oxygen will be less in that. Okay. So solubility will decrease if the temperature is high. Chemical reactions are temperature controlled. Color, the unit of color is 5 NTU actually. Nephthalmeter turbidity unit. NTU we generally 5 to NTU will be the acceptable limit for the drinking water. Apparent color, the color reason because of the suspended solids. So we will be having a dissolved solid present in the water. We will be having suspended solids present in the water because of this water will look in a various colors like yellowish color and all that, right? So colors are measured in Burgess scales like platinum scales. We can say the true color units, a TCU. We will be using a tintometer device for measuring this color in a water. Okay, so TCU will be the unit. Yeah, you can say the NTU also. There are some methods for it. So 1 TCU will be the 1 mg of platinum as a platinate iron mixed in 1 liter of distilled water. There is the testing parameters. You have to do it in the laboratory. So if you are taking a 1 mg of platinum-based chloriplatinated iron mixed in a 1 liter of distilled water, if you are mixing this portion, 1 mg portion, then the value will be called as 1 TCU. Okay. So color produced as a 1 TCU, drinking water less than 5 TCU will be acceptable. If 4 mg mixed in 8 liter water, then 4 divided by 8, 0.5 TCU, mass divided by volume, you can estimate this number. Okay. If it is telling like a 4 mg platinum based iron is mixed in a 8 liter of distilled water, then 0.5 will be the TCU for it. Okay. Turbidity, you must be doing all the tests in environmental engineering laboratory. I will be focusing more on units. I will be focusing how to estimate it and what are the devices that you are using it from the gate point of view. So generally they ask it, they will give some numbers and they will ask, okay, 4 mg iron is mixed in that much quantity of water. How you will calculate the unit, what will be the color of this water, right? So you must understand what is the unit first. So TCU will be the unit, so 0.84 divided by mass divided by volume. You can calculate it. And you must understand what is the acceptable limit for the drinking. So we are taking 0 to 5 TCU. Second is the turbidity. Turbidity causes because of the suspended solid present in the water and colloidal solids present in the water. Because of this this turbidity will be the main reason. And quantity of solid matter present in the suspension rate states turbidity is a measure of light emitting properties of water, and turbidity test is used to indicate is a measure of light emitting property of water, and turbidity test is used to indicate the quality of waste discharge with respect to colloidal matters. Okay, there's a turbidity meter in a laboratory. You can test the turbidity of water sample. You have to check the light emitting radiations, how much light is emitted through the sample, water sample. There's a turbidity meter in the laboratory, you can test it, okay? And based on this, how much portion is scattered in the light, how much portion is going without any deflection, right? So you can understand that. You can get the number in NTU. So turbidity depend upon the strength of the seaways, and if you are if I'm talking about the wastewater and seaways content, the turbidity of course depend on the strength of the seaways, right? There are the methods for turbidity test. One is the turbidity rod method, another one is the ejection turbidity meter. Two devices that you use to use it. The small particles will be having a high turbidity, more surface area is required, and larger particles should be having a small turbidity. It is reverse actually. Turbidity is the surface phenomena, and dissolved particles does not pass any surface area. Turbidity is the measure of resistance offered by particle in water to the passage of the light through water. Okay, and unit silica scale as a turbidity unit is called as the NTU, and 1 NTU will be the 1 mg of finely divided silica mixed in 1 liter of distilled water. Okay, same like our TCU. 1 mg of finely divided silica mixed water will be mixed in a 1 liter of distilled water. Then so 1 divided by 1, so 1 NTU will be the unit for it. So turbidity is measured in the turbidity meter. You can see there's a laser light emitted source, light trapping water sample you are giving in between, and scattered light, electric power output in proportion to intensity of the scattered light, and there's a photo cell on the top, and you can detect this. The numbers will be displayed on the screen itself. This you must be doing this experiment in your laboratory. You are taking this angle 90 degree. At a 90 degree, how much light is emitted, how much light is scattered. Through this you can capture the number. So two ways we are having it, as I told you, turbidity meter. Turbidity meter is based on light absorption. First is ejection turbidity meter, another one is the ejection turbidity meter for high turbidity, and third one is the Baylis meter for low turbidity. Okay. So 0 to 2 ZTU up to the 5 ZTU, yeah, you can say the NTU will be acceptable limit for the Baylis meter low turbidity. We have a left flow meter. Left flow meter is based on light scattering phenomena, and turbidity meter based on light absorption phenomena. Okay, that you have to remind it. Measures turbidity in NTU. Left flow meter turbidity unit. 1 NTU is equal to 1 mg of formangine polymer mixed in 1 liter of distilled water. Sometimes we call it as the FTU also. So this is the turbidity meter apparatus. Light source, light emitting. There's object, water sample given here. How much light is scattered? There's a detector placed here, and through this diode, you will get the number in digital stream. 22 NTU it is displaying, so you will get the turbidity directly. How much portion is scattered at 90 degree angle? That you are capturing it here. So you can understand the how much turbid water it is. What is the portion of suspended solid and dissolved solid present in the water, and colloidal solid present in the water. That is important. Okay. Second is the electrical conductivity. How many people are there? Three. Okay. So water characteristics I will complete today, because we will be having a very limited number of classes, and syllabus is very large. So we have a time constraint. That's why we are trying to cover up in 2 hours maximum portion. And I will be taking some extra lectures. Through this, I will be solving some numericals, short numericals. We'll take from the from the gate perspective point of view. So you will get some exercise how quickly you will solve the numericals with accuracy. Okay, that portion we will cover it later. The third thing is the electrical conductivity. These are all, whatever I'm discussing, these are all the physical parameters actually. And these things are common for the wastewater as well as the water only, municipal water. So electrical conductivity is a measure of water capacity to convey electric current. Electrical conductivity is commonly used for indicating. You just think like we are revising the concept, okay? Pranati, Jayashurya, two are there only. Jayashurya and Pranati. Okay. So electrical conductivity is a measure of water capacity to convey electric current. Electrical conduction is commonly used for indicating the total concentration of ionized constituents of a neutral water, the electrical resistance of sample, and you can say the potassium chloride solution of non-conductance are measured at the same temperature, and electrical conductance increases as the concentration of dissolved matters increases, and the value will depend on the value of various dissolved substances. This measurement is expressed in terms of we can say the microsiemens per centimeter at 25 degrees Celsius temperature. The target water quality ranges 0 to 70. The more ion presence in a water, such as that of carbonate, bicarbonate, chloride, sulfate, nitrate, sodium, potassium, calcium, magnesium, the more electricity can be conducted by the water. That is the concept for conductivity. Another one is order. The value should be less than 3 TON. Threshold order number. The unit of order will be threshold order number. So order and taste can be measured through this. The order is measured by the device called as osmoscope. The capacity of inhaling 200 ml diluted sample is used in this. The threshold order number will be the unit for it. TON is dilution ratio at which order is just detected. So how to get the number of TON? A plus B divided by A. Suppose A plus B, how much ml sample we are taking it? Inhaling capacity of sample is 200 ml. Capacity of the device. A is the volume of water sample that you are going to take it, is used in dilution. And B is the volume of distilled water. So A is how much water sample you are going to mix with the distilled water. So suppose 50 ml water we are having it, and 10 ml of water sample you are using as a dilution. If you mix with that 10 ratio 50, and then how much total quantity of water now? A plus B, you can take it. So TON you can calculate based on this. So TON will be, so 200 ml sample divided by how much water you are going to mix it. Suppose 15 ml you are taking it. So 200 divided by 15 will give the TON number. So through this order you can identify through this. Sometimes we call it as a flavored threshold number also. Suppose there is a sample given here, A and B, 5 ml sample A, B 195. So 5 plus 195, 200. A plus B will be 200 here. So 200 divided by 5 will give the TON number. Here 190 plus 10, 200 divided by 10 gives the TON number. 185 plus 15, 200. 200 divided by 15 will give this number, TON number. Okay, so these are all the physical characteristics that we have discussed it. Now we will move for the chemical characteristics of water. So chemical characteristics of water, I'll be talking majorly about the solids, total solids, suspended solid, dissolved solids, right? We'll be talking about the chlorides. I will be talking about the hardness. I will be talking about the pH values, metal in other substances, nitrogen in its components, and dissolved gases. I'll be talking about the BOD and COD also in the chemical characteristics. So how to measure the total solids? If you have done in laboratory test in environmental engineering lab, we are measuring the total dissolved solids, total suspended solids, and how much suspended solids are available, and TDS and all that. That we have a test there in the environmental engineering laboratory. So first we have to understand what is colloidal solids, what is suspended solids, what is total dissolved solids. The size I have already explained in the previous slides. Here size I have explained. Where is it? Not here. Size I have explained for the colloidal impurities, dissolved impurities, and suspended impurities. So these impurities are very yeah. So chemical characteristics, first you have to understand what are the size of colloidal substances, what are the size of suspended solids and total dissolved solids, and how to identify that, how to measure these in laboratories, what are the how much percentage, how much an mg per liter, how much dissolved solids are present in a water, right? So there's a method called as gravimetric measure, a weight measurement. There's one method. Through this, you can identify how much colloidal substances are available, how much suspended solids are available, how much total dissolved solids are available. So residue left after evaporation is called as solids in water. So 1 mg per liter is equal to 1 ppm. That is a common unit that you are going to take it throughout the whole analysis. And total solids equal to final weight after oven dried. Generally, your oven dried conditions you are taking at a 103 degrees Celsius temperature here, and you are putting this leftover waste for at least for 4 to 5 hours. Okay, so what you will do it to the gravimetric method. Once you evaporate a solution, once you evaporate this this water sample, of course water will be evaporated. Waterable residue will come in the bottom. There will be some china dish apparatus you are going to use it, cup kind of things, and you are evaporating this water on a very high temperature. So what will happen? Whatever the solids will be there, what you are going to do it, you are taking china cups, 4 or 5 china cups, you are putting a water in that, and you are putting in a furnace having a temperature 103 degrees Celsius, and you are putting this this china dish at least for the 4 to 5 hours, and water will be evaporated, of course, and whatever the solids will be there, initial weight you have to take it before putting this sample into the furnace, into the oven. You have to take the initial weight, that is W1, and then after 4 to 5 hours you can take it out and you again measure this China dish wall. Okay, weight you have to do it. And then W2 minus W1 divided by volume, you will get the total solids available in the water. Okay, it's a simple calculation. So what is the initial weight? What was the final weight? So initial weight minus final weight divided by the volume ml of sample that you have taken, you will get the total solids present in the water. Colloidal solids are finely divided solids remaining either in a solution or maybe in a suspension form. It cannot be visible actually. So in suspended solids, you can do the same analysis, W2 minus W1 divided by volume of sample that you have taken it. And total dissolved solids limit should be less than 500 mg per liter. It should not be, it should cost that much. So one of the most important characteristics of seaways is the solid content. And seaways, if I'm talking about seaways water, so seaways normally contain 99% of water and 1% solid, if you see the seaways estimation. So design a biological unit in water pollution control methods which depend on the concentration of the organic matter, organic solids, and a grid chamber and sedimentation tank design also, which depend on the quantity of inorganic and organic settleable solids present in a water. So of course the importance in designing for the various unit operation for these colloidal solids, suspended solids, and total dissolved solids is high. So if you identify the proper number, then based on this you can accurately design all the grid chambers and sedimentation tanks and all that. There are some dissolved inorganic solids also are to be considered in the design of land treatment of the seaways, that is in the disposal of seaways. I will talk about it. Dissolved solids are those which will remain dissolved in seaways just in water. Strength of the nutrients if of this is called as dissolved solids. Okay. And the dissolved solid play a very important role in deciding the strength of the seaways because it creates a nuisance. If it is disposed in an untreated manner, it gives a lot of problems. Suspended solids are those which are in suspension and are floating in a seaways, and they are further classified as classified into like we can say the suspended solids will be, if you want to identify the suspended solids, if you have a total solids value, if you minus it the dissolved solids value, then you will get the suspended solids value, right? So SS will be TS minus DS. For measuring the suspended solids in a laboratory, you'll be using a hot air oven. The temperature you are setting 103 degrees Celsius, and you are putting this sample for at least for 4 to 5 hours. After the sample is dried off, you are again going to measure the weight. Okay. You're using MHOF cones also for doing this laboratory test. There are some settleable solids also which settle down at the bottom of an MHOF cone and are an approximately measure of the quality of the sludge that will be removed by the sediment. So if you want to measure a settleable solid, you can use MHOF cones. There are some non-settleable solids are those are in colloidal in nature and can be removed by chemical treatment. There are some fixed solids and volatile solids also. The fixed solids are also called as inorganic solid consisting of minerals and salts, which include sand, gravel, debris, dissolved salts, etc. They constitute about 55% of the total solids and are not harmful in sewage treatment operations and required only mechanical treatment appliances such as screens for their removal. Okay, so fixed solids are not much hazardous for the sewage treatment for the sewage water. Volatile solids, we used muffled furnace for it. Temperature range you have to set at least 700 degrees Celsius to 800 degrees Celsius. They are also called as organic solids or ignited solids, consisting of organic matter such as carbohydrates, fats, oil, and constitutes about 45% of the total solids, and commonly used in the analysis of wastewater sludge to measure their biological stability. So volatile solid, if you want to measure it, if you have a total solids value, if you minus fixed solids, you will get the volatile solids value. So the importance in terms of sewage treatment plants and why we are removing these particles, why we are removing volatile solids and fixed solids, and how to test it, how to measure that percentage of volatile solids and fixed solids, then you can do it in the laboratory. Okay. The sample for the volatile solids, you are going to put it under the in a muffled furnace using setting the temperature of 700 to 800 degrees Celsius for 3 to 4 hours. Okay. So these are the chemical characteristics for the suspended solids, colloidal solids, and volatile solids. All that, how to identify that, how to measure that, how to determine the quantity. And we have a pH value. pH is, you already know about the pH. pH is one of the most important parameter of water quality. It is defined as the negative logarithm of the hydrogen ion concentration. So it is a dimensionless number indicating the strength of an water, whether it is acidic and basic or maybe the neutral solution. So based on this, you can decide it. The limit of pH is 0 to 14. So if you see the hydrogen ion, the water molecules compound actually. So two hydrogen ion molecules in oxygen. So OH ions will be negatively charged, as we called as anions, and H will be the hydrogen positively charged. Okay, that is cations. So pH will be equal to minus log H, logarithmic value of 10H, and then log 1 by H, and if you go for the calculations, and finally POH will be mine. You can write it in such a manner also. And the ionization constant, you need to calculate it. K H positive and concentration of O divided by H2O concentration. Generally, you are taking H2O concentration to 1 here for the pure water conditions at 4 degree. Then K value you will get it 10 to the minus 4 mole per liter. So pH of water is the measure of how acidic and basic water it is. And acidic water contains extra hydrogen ions, H positive, and basic water contains extra hydroxyl ion, that is OH negatively charged. pH ranges is 0 to 14, 7 being neutral, pH of less than 7 indicates acidity, pH of greater than 7 indicates as a base solution. So pure water is a neutral solution. The pH is close to 7 at 25 degrees Celsius. Normal rainfall has a pH of approximately 5.6, slightly acidic, owing to atmospheric carbon dioxide gases. Safe range of pH for drinking water should be 6.5 to 8.5 for domestic use, and living organisms needed. And what are the methods to calibrate the pH in laboratory? We will be having a calorimetry method where you are using a filter paper, a pH paper. There is the electrometric method also. We are using a pH meter, and through the titration also you can measure the pH. Okay, there are 3 methods. Through the pH paper you can do it. Universal indicator method is also there. Through the titration you can do it. And then there is a pH meter. Through this also you can measure the exact value of the pH in a sample. Very simple methods. Pranati is there. Pranati and Jasurya. Only 2 people left. 2 people are there in the class. I have to record it for the 2 hours, so very less attendance recorded. I don't know why. Chlorides is also need to determine it, and the safety concern, you can check how much value is required for the chlorides available in water, and it should not exceed 250 mg per liter for the safe drinking. So chlorides occur naturally in the groundwater, streams and lakes, but the presence of relatively high chloride concentration in fresh water, about 250 mg per liter, can be acceptable. In environmental engineering laboratory, we are testing residual chlorine and chloride test. We are doing it there. May indicate wastewater pollution. Chlorides may enter surface water from the several sources, including chloride containing rocks, agriculture runoff, and wastewater. So chloride ion is negatively charged in drinking water. So do not cause any harmful effect on public health, but high concentration can cause an unpleasant salty taste for most people. So chloride are not and sodium chloride may impart at 250 mg per taste until reaching the level of 1000 mg per liter. So standard for public health, public drinking, the standard is given it should not do not cross the 250 mg per liter. There are many methods to measure the chloride concentration in water, but the normal one is the titration method by silver nitrate that we have to do in the laboratory. Okay. So chlorine does not, if I'm going to the disinfecting purpose, the chlorine, residual chlorine, if you want to test it. So as I told you, chlorine is a very good disinfectant. It can kill the pathogens or make inactive the bacteria. And so chlorine, if you see the chlorine gas does not occur naturally in a water, but it is added to water and wastewater for disinfecting purpose, for killing the bacteria, pathogens, and viruses. And while chlorine itself is a toxic gas, in a dilute aqueous solution, it is not harmful for the human health. In drinking water, a residual of about 0.2 mg per liter is optimal. The residual concentration which is maintained in the water distribution system ensures good quality sanitary quality of water. So chlorine can reach with organics in water, forming toxins and how it will kill the pathogen. So chlorine can trimethanes or THMS, we can say that in short, which are carcinogens, such as chloroform. And chloroform, again, it's kind of disinfectant actually. The presence of free chlorine, also known as chlorine residual, free chlorine residuals, and residual chlorine in drinking water indicates that, number first, a sufficient amount of chlorine was added initially to the water to inactivate the bacteria and some viruses that causes the diarrhea diseases and all that. Okay. Second is the water is protected from recontamination during storage. So there are two objectives for adding a free chlorine in the water. Once the water is treated fully, so there is a operation where we are adding a chlorine in the initial stage, in the pre-chlorination stage. Then after water will be filtered, you are going for the post-chlorination. And then residual chlorine amount also you are going to add it throughout in the distribution network. So there are two objectives. You don't want like any bacterial growth will happen inside the pipe network, and you want to, because sometimes what will happen, water will be in a stagnant stage in a OHSR for a certain duration. So if the pathogens and bacterial growth happens inside of water, is not safe for drinking. So there is a chlorine was added initially, so 0.4 to 0.5 mg per liter you can dissolve as a residual chlorine for it. Okay, in a treated water. Was added initially to the water to inactive the bacteria and some viruses that can cause the diarrhea of diseases. And the water is protected from the recontamination during storage. As I told you, the presence of free chlorine in drinking water is correlated with the absence of most diseasing causes organisms. Thus, is a measure of the potability of the water. So, chlorine residual is normally measured by the color comparator test kit, or we can say the spectrophotometer can be used for determining the residual chlorine. So, to the titration, if you want to calculate the value, you determine the value in the laboratory. The amount of residual chlorine in mg per liter you can get it. How much ml of titrant you are doing in the titration, and normality of titrant multiply by 1000 multiply with the molecular weight of that solution what you are going to take it, right? And how much ml of sample you are consuming it. available chlorine in such a manner also you can check it, and the percentage of available chlorine also, the weight of available chlorine divided by weight of bleaching powder multiplied with 100 percentage of available chlorine available in a water sample. Likewise, acidity and alkalinity also play a very important role. You have to check the whether water is acidic and neutral or basic, right? And you have to check the two types of there are mineral acidity that you have to check it, and that you have to check the total acidity. And then we have two types. If you are talking about the alkalinity point of view, we will be having two types of alkalinities. One is the phenolphthalein alkalinity, and the one is the total alkalinity. Okay. So mineral acidity and total acidity, two types of acidity, and then phenolphthalein alkalinity and total alkalinity. You have to check it. If you are going for the laboratory testing for alkalinity and acidity, so the titration you can do it, and you can use the various solvent and solute, and then you can conduct a test. Hardness is also again we can say the very important parameters, chemical characteristics of a water. Hardness needs to be checked, and the water should not be very hard, because the hardness create a lot of problem for the corrosion and all that, and it again create a problem for the human health also. It is not advisable. So generally the unit is mg per liter or ppm, same. So hardness is termed used in express the properties of highly mineralized water. The dissolved minerals in water cause problems such as scale deposits in hot water pipes and difficulty in producing leather with soap. Calcium water limestone deposits, and these need sulfates and sometimes citrates. Generally, the groundwater is harder than surface water. There are the two types of hardness we will talk here. One is the temporary hardness, which is due to the carbonates and bicarbonates, can be removed by boiling. So calcium bicarbonate and magnesium bicarbonate. During boiling, bicarbonates are decomposed to yield insoluble carbonates or hydroxide, which are deposits as a crust at the bottom of the vessel and can be removed. And if you are talking about the permanent hardness, which is remaining after boiling, is caused mainly because of the sulfates and chlorides, which cannot remove by boiling in other operations, right? So water with more than 300 mg per liter of hardness is generally considered to be hard. More than 150 mg per liter of water hardness is mg per liter of hardness is noticed by most people, and water with less than 75 mg per liter is considered to be soft. So if the hardness causes because of the carbonate and bicarbonate present of calcium and magnesium called as temporary hardness, the hardness which is causing because of the sulfates and chlorides available, the carbonates and the available in the water is called as a permanent hardness. Okay, so I will be coming here. So what will be the total hardness, temporary hardness plus permanent hardness? So some of both the things we call as total hardness. So this permanent hardness is due to the dissolved chlorides and sulfate and nitrate of calcium and magnesium present in water. And these salts are calcium chloride, magnesium chloride, calcium sulfate, magnesium sulfate, calcium binitrate, magnesium binitrate. Okay, so these are the main reasons for the permanent hardness. And now, how to remove this permanent hardness from the water? The permanent hardness removing methods I will come later also while the treatment is concerned. While I'm moving for that water treatment part, I'll be going in more detail about the permanent hardness methods. But just for the quickly, you must understand there is a lime soda methods, zeolite methods, ion exchange methods, and demineralization methods available for removing the permanent hardness. So there are three methods to determine the total hardness. If you want to consider the total hardness, there is a Clark method. These are the scientist names, Henner methods, and there is a Vernet methods. So from the health point of view, hardness up to 500 mg per liter is safe, but more than it causes laxative effects. And hardness is normally determined by titration with the ethyl diamine tetraacetic acid (EDTA) methods. Yeah, Ariocrem black and blue indicators you can use it. It is usually expressed in mg per liter of CaCO3. Okay. So I'm not going for the detail for these methods. Once I will move for the treatment part, I will be going in detail about the lime soda method, zeolite method, because treatment we have not yet started. Here our objective just only to determine the hardness component. What is the percentage of hardness is available in water? Okay. So there are three methods: clock method, Handel method, and these methods. I'm not going for the details. Okay. So okay, in the next lectures I will again continue for this. And if you're going for the titration method, these are the formulas that total hardness as mg per liter as CaCO3 equivalent. You can go for it. So ml of EDTA, how much you are taking it as a V1, volume you can take it, multiply with normality of EDTA, multiply with 15 to 1,000, divide by how much ml of sample you are going to take it, consume it. And there is a calcium hardness, this respective same formula. And the magnesium hardness mg per liter as a CaCO3, you can get it if you have a total hardness number minus calcium hardness, you will get the magnesium hardness. But the total hardness will be the magnesium hardness plus calcium hardness. Yeah, you can say the permanent hardness plus temporary hardness. Okay. So these are the all chemical characteristics. Some nutrients are also there that you have to cadmium, magnesium, iron. You have to remove it, right? You have to check the how much iron is available in the water, how much cadmium, how much lead is available, and how much nitrate is available, how much nitrite is available in the water, and how much carbon dioxide is available in the water. Characteristics of water. The next is dissolved oxygen. It's very important for the microbial growth, for the organic matter decomposition. Dissolved oxygen play a very important role, and for the survival of aquatic life also dissolved oxygen is required. Generally 4 mg per liter of dissolved oxygen is required for the survival of the aquatic life. So dissolved oxygen is the amount of oxygen dissolved in a water measured in milligram per liter. The ability of water to hold oxygen in solution is inversely proportional to the temperature of the water. If temperature is higher, dissolved oxygen is less. The solubility of oxygen in water decreases with the high temperature, and dissolved oxygen is considered to be one of the most important parameters of water quality in streams, rivers, and lakes. It is the key test of water pollution. The higher the concentration of the dissolved oxygen, the better the water quality. Oxygen is slightly soluble in water and very sensitive to temperature. For example, the saturation concentration at 20 degrees Celsius is about 9 mg per liter. At 0 degrees Celsius, it will be 14.6 mg per liter. So cold water will be having a more amount of dissolved oxygen. Okay. At 20 degrees Celsius, you can see the 9 mg per liter. If it is 0 degrees Celsius, it is the percentage of the amount of dissolved oxygen will increase to 14.6. The actual amount of dissolved oxygen varies depending on pressure, temperature, and salinity of the water. And dissolved oxygen has no direct effect on public health, but drinking water with very little or no oxygen test dissolved oxygen has no direct effect on public health, but drinking water with very little or no oxygen taste uh, uh, called as, like we can say, the unpalatable to the some people. It is not acceptable. So there is it creates a problem. There is no dissolved oxygen in the water. Again, it creates a problem for the human health, right? So for the aquatic life, at least dissolved oxygen should be there in water because it is required for their organic matter decomposition and food stabilization process, right? So there are three main methods used for measuring dissolved oxygen concentration. One is the calorimetric methods, which is quick and inexpensive. The second one is the Winkler titration method, traditional method, and we have a electrometric method also, If dissolved oxygen droplets, it will be difficult to many aquatic organisms for the survival. Okay. We'll be having a biochemical oxygen demand. Biochemical oxygen demand, again, it will depend on the dissolved oxygen also. So if you define the biochemical oxygen demand, the BOD is a measure of oxygen required to oxidize the organic matter present in a water sample through the action of microorganisms contained in a sample. It is determined by incubating a water sample and measuring the decrease of dissolved oxygen as bacteria decompose these materials, because bacteria consume these oxygen and they require oxygen to biodegrade the organic matter. And how much oxygen is consumed to break down the organic matter, this amount is called as biochemical oxygen demand. The incubation period is given generally 5 days at 20 degrees Celsius temperature. So there is aerobic oxidation occurs inside, and in a 5 days incubation period at 20 degrees Celsius, we assume that the 99% organic matter will stabilize biologically, right? So complete biodegradation will happen. So generally 21 days are required for the 100% decomposition of organic matter. So we call it as BOD5 and BOD21, right? So BOD21 means 21 days of incubation period you are giving it, and maintaining temperature 20 degrees Celsius now. Okay. So the organics are broken down into simpler compounds such as carbon dioxide and H2O, and the microbes use their energy released for their growth and reproduction. So more microbial growth will happen because the reproduction actions and growth of bacteria will happen inside, because they are bacteria and these microorganisms are consuming the oxygen, and then all will take place, and microbes will form. So within this process occurs in water, the oxygen consumed is the dissolved oxygen in the water. If oxygen is not continuously replaced by natural or artificial means in the water, the dissolved oxygen concentration will reduce as the microbes decompose the organic matter, and then reaeration will happen there, right? So this needs for oxygen is called the biochemical oxygen demand. The more organic matter material there in the water, the higher the BOD used by the microbes will be. BOD is used as a measure of power of seaways. A strong seaways has a high BOD and weak seaways has a low BOD. Okay. And there's a BOD test, how to conduct that. So BOD for 5 days and BOD for the saturation days or 21 days, how much we are taking it. 100% decomposition of organic matter in BODL. The quantity of oxygen used in a specific volume of water to fully decompose or stabilize all biodegradable organic substances is called as the ultimate BOD or BODL. And this is called as the BOD curve, where this is and which can be expressed mathematically by the following equation. BOD at the respective time is equal to BOD L, ultimate BOD, multiplied with 1 minus 10 to the power minus KT. Okay. So BOD T is the BOD at any time, T, mg per liter. BODL is the ultimate BOD, mg per liter. K is a constant representing the rate of the BOD reaction, and T is the time. The value of the constant rate K depend upon the time and the type of organic matter and the type of microbes entering the BOD. So this is the BOD curve, and you can determine the BOD by using this titration. There's an initial concentration of dissolved oxygen in mg per liter. So we are taking volume of Na2S2O3, multiplication of normality of this solution, multiply with molecular weight, multiply with 1000 divided by 1000, 1 ml of sample, and immediate DOD, initial DOD, DO, and then final DO after 5 days. You are taking it and you are doing this calculation, and DO initial minus DO5 divided by the dilution factor, you will get the present BOD available in water in mg per liter. So P is the dilution factor, DO is the dissolved oxygen of the diluted solution after preparation of 5 days BOD sample. And D5 is the dissolved oxygen of the diluted solution after 5 days incubation period. So BOD5 is calculated by using dilution method. There is unseeded BOD and there is a seeded BOD. Unseeded BOD will be the BOD5. So initial DO minus final DO divided by dilution factor, and then final and seeded BOD5 also you can get it. DO minus DO5 minus BO minus B5 into F by P. These are the DO is the DO of diluted seed sample after preparation. BO B5 is the dissolved oxygen of diluted seed sample after 5 days incubation mg per liter. F is the ratio of the seed volume and dilution seeds to seed volume and BOD test on seeds. And the chemical oxygen demands, there's the last. So a strong chemical oxidizing agent is used in acidic mediums to measure the oxygen required of organic matter that can be oxidized. CO2 test is involved in an acidic oxidation of potassium dichromate. So what is chemical oxygen demand? Chemical oxygen demand is nothing but the amount of oxygen required to decompose the organic and inorganic matter together. So this amount of oxygen is called as chemical oxygen demand. So chemical oxygen demand is demand, you can write it as the amount of oxygen required for the chemical oxidation of organic matter in wastewater with the help of a strong oxidizing agent such as KMnO4, or you can take as potassium dichromate. So CO2 determination has advantage over BOD determination. The result can be obtained by CO2 test within 3 hours, whereas it takes 5 days for BOD test. Further, the test is relatively easy, gives reproducible results, and it is not affected by COD is a parameter measure all organics, the biodegradable as well as non-biodegradable substances. But chemicals using strong oxidizing chemicals, potassium dichromate, sulfuric acids, and heat, and the results can be available in just 2 hours. So there's the advantage. And CO2 value are always higher than BOD values for the same sample. It is expressed in milligram per liter, as referred to as ppm, part per million, which indicates the mass of oxygen consumed per liter of solution. CO2 refers the requirement of dissolved oxygen for the oxidation of organic and inorganic constituents both. There is a method for determining the COD. You can go for the spectrophotometry method to determine the COD, and there is the titrimetry method. So the organic, I'm just going to bind up, just done actually. The organic matter get oxidized completely by using potassium dichromate in the presence of H2SO4 to produce the CO2 and H2O as a byproduct, and the excess K2Cr2O2O7 potassium dichromate remaining after the reaction is treated with ferrous ammonium sulfate, and the dichromate is consumed to give the oxygen required for the oxidation of the organic matter. So biological characteristics for the pathogens and microbial growth determination. I don't have time. I will just check how much time it will take. Yeah, it will not take too much of time. I will finish this biological characteristics of MPN also. So the biological characteristics means you are going to determine the pathogens, bacteria available in a numbers, and whether the bacteria and viruses and pathogens are available in water or not, that you are going to test it. Okay. So there is a microbial examination of water. There is a testing procedure. There are 2 tests. One is the qualitative test. Another one is the quantitative test. The qualitative test, whether the microorganisms are present or not. Quantitative test, quantity, the amount of organisms present. Those 2 tests we have to do it. With the qualitative test, we will be having 2 tests again. Plate count method. Another one is the membrane filter technique. I'm talking about the plate count method. The substrate is provided to trigger growth in Petri dish. There is one component Petri dish, you have to take it as a container, as a vessel you can take it. Petri dish is kept in incubation at 37 degrees Celsius temperature to maintain the warm condition for the growth. Minimum time for microbial growth is provided as 24 hours. Okay. So the condition is you have to put the sample for the incubation of 37 degrees Celsius temperature, and the minimum time for microbial growth should be provided 24 hours. Second is the membrane filter technique. Filter papers which can trap even viruses is pre-coated with the food, and after passing with the non-volume of water samples sucked, and the membrane filter papers are incubated again like same as the 37 degrees Celsius temperature for minimum 24 hours. The presence of purple dots and black dots ensures the presence of microorganisms. So through the qualitative test, you can identify whether the bacteria and microorganisms are present or not. The second one is the quantitative test. Quantitative test to identify to get the how much number count, what is the quantity of amount of organisms present in a water sample. Through the quantitative test you can do it. So there's two tests here. One is the E. coli test. E. coli test, there's one Escherichia, we can say the coli. E. coli organism belongs to the coliform group of bacteria. There's the types of bacteria, and it is non-pathogens. E. coli organisms is present in intestines of warm-blood animals, including human, and these are responsible for converting food into the energy and waste product. And these are like some of the pathogens or bacteria are good for the health, good for the microbial, like it helps to digest your food. So, so these are responsible for these E. coli bacteria are some of the bacteria are good, some of the bacteria are bad actually for the human. So these bacteria helps to convert the food into the energy and waste product. Three stages. Number first is presumptive stage, second is confirmed stage, third one is the completed stage. There are two standards for measuring this. Drinking water standards, E. coli index, that is for the drinking water it should be 0 E. coli index, and MPN number. It should not be greater than 1 number divided by 100 ml. In 100 ml sample, 1 bacteria as a 1 number is okay. If it is greater than, then it is not acceptable. So there's a unit for it. So E. coli index and MPN number, both are important. You have to check it. Like if you are going for the lactose fermentation, at 36 and 70 degrees Celsius incubation period for 24 hours, E. coli tests are finally termed as unit E. coli index. So MPN, most probable number, is generally called as most probable number. So in lactose fermentation, you can identify how many bacteria are consuming there. If you put this solution, your sample for 37 degrees Celsius incubation in 24 hours, then E. coli test can be conducted and you can get the number. E. coli index is the actually. So E. coli index is the reciprocal of the smallest quantity of sample which will give the positive result. One number in 100 ml sample, MPN, represents the bacterial density. If I'm talking about the bacterial density, the E. coli index, what is the E. coli index? Is the reciprocal of the smallest quantity of sample which will give positive result. And one number in 100 ml sample, MPN, represents the bacterial density present, which is most likely to be present in the given water sample for the given test result. Okay, so these are the things. These are the CPHU drinking water standards. Color, order, turbidity, solubility, salt, TDS, pH, hardness, calcium, chloride, sulfates, magnesium, nitrates, fluoride, alkalinity, choline, and coliforms. These are the desirable values, and there's the maximum permissible values are given. These are effects if not controlled. These are effects on human health as well as on the environment. Okay, so thank you for the listening, and thank you for your patience for listening to the lecture. So, and thank you CMR Institute of Technology for providing me opportunity for this valuable lecture, and I get a chance to furnish my knowledge, and I get a chance to explore myself in this environmental engineering field. Thank you AICTE also for providing me this opportunity for this GATE classes. Time is very short, so I will try the another part for the treatment part of wastewater engineering and water treatment plant, municipal water, both together. In the next lecture of series, I will try to complete the portion, and I will try to make it short. Okay. So thank you once again for listening, and thank you for the patience.